Ja, dan doen wij vast wat praten. En ook deze zou dan weer te horen moeten zijn. Zo, 1, 2, ha, ja. Zo, ha, ja. Zo, ha.
All right, everybody, we're about to start. Are there any other speakers in the room already? Okay. Uh, I'll mention this just so everybody knows, but uh, for the speakers, I'm showing two cards. For the 10-minute talks, it means that you have 3 minutes left and then 1 minute left. And for the 3 minutes talk, it means that you have 10 minutes left and then 6 minutes left. And yeah, just be aware of that. And if you are about to present, please come by so you can get mic'd up before we start. All right. We'll have a couple of minutes, so we'll wait for the people to chime in. No, it's just yeah, when you get up. Yeah. All right, so we're gonna get started with Rasha. Rasha is at Julia Hub, and he'll be presenting on building desktop applications, which he has been maintaining for Julia Hub and Pumas for some time. So please take it away.
Sure. Good morning, everyone. So let's begin with what an enterprise-grade integrated Julia binary means. So let's say you have an application, it's written in Julia. So obviously it uses Julia packages, and you do have artifacts and dependents and prerequisites for this binary. And you want this binary to ship to an enterprise or any public medium. And so in this talk, we will provide guidelines on what you should take care while shipping your Julia application. So let's begin with this. And so our talk is divided into multiple. Our talk, we do have 3 major operating systems: Linux, Mac, and Windows. So we will start off with the common features. These common features are applicable for all 3 of them, just as in the slide says. So the first feature is obvious. You have to extract your Julia binary. You're shipping the Julia binary. You don't expect the customer to have the Julia binary, of course. And you're shipping your sys image or a package image, because you don't want your customer to wait until your packages get precompiled. So you ship a sys image or a package image if it is 1.11 and above, since package images are now it's not dependent on a single system. So, and of course there are other prerequisites as well, like artifacts, registries, and management files or third-party libraries. So we do have pre-install and post-install scripts. So let's talk about that. So pre-install scripts are the ones who check the prerequisites for your installer. You don't want your user to install the software and then figure out, okay, I needed a .NET framework, I needed this particular library to be pre-installed, but and now your application is not working. So you don't want to be in that situation. So you check for these prerequisites during the installation. That's where the prerequisite install script comes in. And of course, the check also applies to whether if you have a 64-bit Windows application and someone is trying to install it on a 32-bit, of course, your pre-install scripts is going to come up in that situation as well and tell the user, okay, you can't install this software because this is made for 64-bit. And the post-install scripts, these are the scripts which you, for example, you write the launcher on the system. Like during the installation, you can't write the launcher like in the binary itself. You have to write it on the system because you need to include the absolute paths. And of course, you do have the uninstaller as well in case of Windows. Uninstaller has to be written on during the installation, and it needs to be registered with Windows registry as well. So these things need to be handled in post-install scripts. This happens after the installation and extraction is done. So the obvious thing with any installer is, of course, you will be asked for the install location. And the one specific thing for your binary is the Julia package server URL. So since you're shipping this to an enterprise or even anything, even for a regular person as well, so enterprises do tend to have sometimes their own private package server, a PKG private package server. They might have an instance of a private package server running on their private cloud. So this is where during the you set up your Julia to point to this cloud and make sure it uses the private package URL and not the public one. Of course, you can default it to pkg.julialang.org, which is the default. If user is just clicking next, and that's what they get. They can still install packages and stuff like that. And I did talk about the prerequisite check. So we not only do this prerequisite check during the installation, we should do it on every launch. That's my opinion, by the way. And we should do it on every launch because a system is a dynamic environment. It can change. Like user would have moved your files, user would have deleted your files. Anything can happen. So there should always be a way to repair your installation. And checking the prerequisite during the launch is the only way to do it. And there are other things as well. Let's imagine the scenario. There's a Windows administrator, and the administrator is installing the binary and is using his admin account. And the Julia depot path, you want it to be in the end user's home directory. And if admin is installing it, it will go to the admin's home directory. And if there is a non-admin who is using the same system, he won't be able to access the installation. So that's where the launch script comes into picture. So if the admin has installed the software and he has logged out from his admin user, now the non-admin comes in, he double clicks on your application. If the launch script checks for the prerequisite, it checks whether the user has the depot path, and the depot path has all your prerequisites, like your artifacts, your package source, everything. If it doesn't, it will copy it for the user. And this is just a one-time thing, and the check is not really taxing on it. But you can do a minor checks, like checking if the file exists, checking if a directory exists, which shouldn't be too much taxing for your startup. And yes, the second one is keeping the original files in the installation directory. Okay. Keeping the original files in the installation directory. So you should always keep the original files in your installation directory because as an archive. Because if the window, like the admin could have installed your app on a mounted network drive, or your profile itself might be a roaming profile where you can log in from any system within the enterprise, but none of your local files are on that system. The local files are on some centralized system. So these are the scenarios where the copying thousands of files from your source to the user's home directory would take a very long time, especially in case of Windows. So yeah, you should be careful on this. So that's the reason you should use compressed archives. You copy the compressed archives to the user home directory, and you extract in there, and yeah, you get your entire depot path that you want the users to run. So yeah, so I will get to the Windows. Windows, you can write the Windows installer using any of these scripting languages, NSIS. Initially, Julia was using NSIS in the past. Now Julia uses InnoScript. And of course, the good old install shield, which has been there for like more than a decade. And the installer options should always depend on the privileges. Like you have a Windows binary, the non-admin is running, the options that you're getting in the installer should be different. And if an admin is running, of course, the options will differ as well. So your installer should not be a static thing, it should be a dynamic one. That's what it says. And yeah, I think I ran out of time. So yeah, and have a good uninstaller. Like you should clean up your files. And code signing your binaries. Okay, I will just skip through these things. Okay, the Linux, what we used to do is we used to have a shell script, a self-extracting shell script. Your entire binary is written into a shell script, which is as a binary. So the user will get a single file, will just execute that file, and everything gets extracted through that file. That's a pretty easy one. And to verify this, you can always use the .asc file. Even Julia uses the same thing. And Mac, .pkg is recommended for your application, and as opposed to a DMG, because pkg gives you more leeway. You have to extract your files in different folders and files, and you do need Apple developer program if you're planning to sign. Of course, you have to sign your binary, and this is definitely required on this. Yeah, so I think I'm up with the time. Yeah, this was my talk.
Do we have any questions from the audience?
So I saw you put quite an emphasis on pre-installation scripts and post-installation scripts.
Yes, I did.
But why are you not delegating that to the bundle itself, like MSIX bundle, for instance, no longer has these scripts, opportunity to have these scripts, but it can put your desktop icon in right place depending on the manifest file how you configure a manifest file.
Oh, my bundle can be like, this is a generic guideline, but the bundle can be an exe or MSI.
Yeah,
and it will have all these features.
Yeah, but what would you do when you don't? Would it be a real issue when you don't have a pre-installation scripts and post-installation scripts?
It might be, but since you're checking for the prerequisite in the launch script, you're covered in that. Even if you ship it as a zip file, your pre-installation, like your launch script, is gonna check for the prerequisite and it's going to copy it for you.
Yeah, but I'm thinking that since the bundle is itself signed, right?
Yeah.
So you just check the signature and it's kind of, I think it's assures that it's the right bundle, right?
Yes.
So, yeah.
Okay, maybe we're up with time. We can catch up on this later, I guess. Yeah. I'm sorry, I couldn't get the question from you.
So let's give Russia another round of applause. All right, so next up we have Andreas, and he's a mathematician translating ideas from geometry, algebraic geometry into software, and so welcome.
Thank you. So I'm going to talk a little bit about Grosvenor bases. So Julia obviously has a lot of capabilities in numeric computing, solving ODEs and all that kind of stuff. So I wanted to show you a little bit about what we can do with the symbolic capabilities that Julia also has. So when we're working with polynomial equations, Grosvenor bases are king. And we have a wonderful package in Julia called grosvenor.jl, which can compute Grosvenor bases of polynomial ideals. However, sometimes our polynomial equations, they have parameters, and grosvenor.jl doesn't account for this. So when we have parameterized polynomial equations, we need parameterized Grosvenor bases. And this is where my new package, parametric Grosvenor bases.jl, comes in. It basically computes Grosvenor bases which spans the different values that these parameters can take on. So I wanted to show you a little example of the kind of stuff that you can do with these parametric Grosvenor bases. So we're going to study what is called the orthic triangle. So if we have a triangle called ABC, we can draw the heights of this triangle from each vertex. We can intersect these heights with the edges of the triangles, and that gives us 3 new points. These 3 new points describe a new triangle. This new triangle is called the orthic triangle. And so we normalize our situation a little bit so that A and B are fixed here, and the only parameter we have is this top point C, which is described by 2 numbers. And then we have these vertices of the orthic triangle here, which are the variables of our system. Now, the crucial insight here is that this can be described as a polynomial ideal. So the first equation here describes that the point P2 sits on the line spanned by A and C. And similarly, the second line describes that the point P3 is on the line spanned by B and C. And, well, the 2 last lines says that the points P2 and P3 are on the heights, so that the line from B to P2 should be orthogonal to the line from A to C. Don't worry about the details here. You can work them out on your own if you want to. But in Julia, we can describe this. So we use Nemo for multivariate polynomials, and well, we set up our parameters here and our variables, and then we describe the ideal. And then we can compute a so-called Gröbner system. So this is a lot. But basically, it describes under what conditions on the parameters does the Gröbner basis look different. So for example, down here, it says if this polynomial equation is 0 and this polynomial equation is non-zero, then b squared is the Gröbner basis of this system. So we are interested in the first case here. Whenever b is non-zero, this is the Gröbner basis of the ideal. And that's sort of the generic case, whenever the triangle is non-degenerate. And we can extract this from the Gröbner system. So we want to ask ourselves, when is the orthic triangle isosceles? So isosceles means that the distance from P1 to P2 is equal to the distance from P1 to P3. And we can answer this because this question can be asked as an ideal question. So when is this polynomial here describing the difference between the 2 distances in the ideal generated by this setup? We can do this in Julia using zero reduction, so we can construct the ideal that we want, and then we can factor the pseudo remainder of this polynomial with regards to this Gröbner basis. And we get a bunch of polynomials, and, well, the inclusion holds whenever this polynomial is 0. So if a squared plus b squared minus 1 is 0, then we have this conclusion. So this corresponds to these 3 lines here. So basically, as we saw, whenever the point C here is in the middle of A and B, obviously the orthic triangle will become isosceles, and we see that here as well, where we have the factor A, that is the x value. And so this plot here gives the entire solution set. But this can be done in all sorts of programming languages that supports multivariable polynomials. We have Macaulay 2, we have Singular, all sorts of languages can solve this problem. So let's look at something that only Julia can solve. So how large can this orthic triangle get relative to the original triangle? We're going to move a little bit quickly around this, but basically we introduce a new variable called r, which describes this ratio between the areas. And then we do a pseudo remainder again. And then we can basically, if we have the values of a and b, we can substitute into this pseudo remainder with those values, and then we can solve the resulting polynomial, which is just a polynomial in one variable. And that gives us the ratio between these 2 areas. This being Julia, we can just find a package that we want to use. We'll use optim here because it's easy. We can call the optimize function, and it gives us the value that the optimal ratio is 2. So the orthic triangle can at most get twice as big as the original triangle, which is not described anywhere, as far as I'm aware. But it's really easy to figure out using Julia. That's it from me. This is a link to the package in question. I would like to thank especially Grosvenor Bases and Alexander, who put in a tremendous amount of work to write that package, and the Nemocast system, which has enabled all this multivariate polynomial computations in Julia. The two QR codes here, the one to the left is to the repository, the one to the right is to another example, because a lot of things can be described using polynomial equations. So this example is looking at the Lotka-Volterra differential equations and trying to find steady states of those. So yeah, thank you very much.
Thank you so much. All right, any questions?
What algorithm do you use to compute the Grosvenor basis?
So we delegate to Grosvenor.jl, but that implements Faucher's F4 algorithm. Yeah.
Any other questions? We have time for one.
Is the package already registered?
It is not registered yet. I'm working on that, but not yet. It will be, though.
All right, so let's thank you, Andra, once more time. And now we have Luca. Luca teaches Julia with Pluto a lot, but he's also a program co-chair for this JuliaCon, so let's welcome all Luca. Also, quickly, for all speakers, the camera is fixed here, so I'm gonna ask you to kind of stay within the range of the table, so you're always on frame.
A, B, C. Okay, seems to work. So, hello everybody, I'm Luca Ferranti, and I will present my talk, Build You a Computational Thinking Like Course for the Greater Good. The title is Easter Egg. It's a reference to a great learning resource. Let me know if you guess where it's from. So, what is the motivation for this? What am I doing? How many of you know the computational thinking with Julia class taught at MIT? Okay. How many of you learned Julia with that? Okay. How many of you wished that class would be available when they learned Julia? So wish they could have learned Julia with that. Cool. Fantastic. And that's exactly my motivation. So there was taught at MIT now for a few years this computational thinking with Julia class. No idea what the red banner is there. Wasn't there this morning. But yeah, so was taught at MIT this class. It uses Pluto. It uses Julia. Has been a huge success. And my thought was basically, oh, that's cool. I want it. And I wanted to use the same for my class, for my teaching. So what I did, I taught a class on fuzzy logic this year. You can see it here. The website looks the same, a bit less content maybe. But yeah, I started building this class, this website, and first I was doing it manually, so I was reverse engineering, modifying the HTML, and then I realized, yeah, but if I ever need to teach another class, I'm at square one again, or square zero if you're a Python person. And also, this doesn't help other people in the world, it only helps me. So I decided, okay, let's take the website, let's reverse engineer that, and let's make a template usable for everyone. And yeah, that's what I did, and that's what I'm talking about today. So the template is available at here. It's called, well, computational thinking template. And I will briefly give an overview of the features and a short live demo, hopefully, of how it works. And then also some discussion and future work of what's on the road. So yeah, that was my motivation in a nutshell. The computational thinking with Julia at MIT was great. Everyone should be able to do that. And if you think about the work of teaching, there's already a lot of work like in making the teaching material engaging, pedagogically sound, and so on and so on. And that should be the only thing that teachers worry about. So the goal of the template is to abstract out all sort of infrastructure stuff, tooling stuff, CI, CD, and all those fancy like acronyms, so that teachers can focus on the most important thing, teaching, and making the teaching material engaging and computationally sound. Yep. And features at the moment, so it's hopefully easy to customize, depends I guess a bit on your level of patience, and it automatically builds the whole website. So the goal is that you simply write the teaching material as Pluto notebook or as markdown file, you dump them in a folder, and then boom, bada bing, bada boom, everything else happens automatically. And now the moment of truth. So if you don't believe me, let's have a live demo and let's see how it goes. So this live demo, it's not exactly like the full experience, the full workflow. I had to simplify a couple of stuff for the sake of time. But the idea is that you go here. This is not even a template repository at the moment, so you just clone the repository. And then you open it, you open the repository somewhere, and then you can start developing with Julia develop.gl, and this will build the website, which we have now here. So this is like the template. So we have coolness 101, short catchy phrase, totet. Oh, I had the Easter egg about the university somewhere, whatever. Yeah. And now let's see if we want to change the class. So suppose we have just cloned the template and we want to start editing. We have a underscore data folder here, which allows to edit the basic informations of the class. So we have a course information.gl, which is a dictionary with basic information. And I can edit, for example, a subtitle. This class teaches something cool. My code, I don't know, 1, 2, 3, 4, semester today. Let's save it. I realized today actually the files in data, in the subfolder data, are not automatically tracked. But what we can do, we can go to the dashboard. So when I start developing, it will open the website and the dashboard. Now let's refresh this. And now you see, this class teaches something cool. And the semester is today with the code 1, 2, 3, 4, 5. Yeah, cool. Now, how does it work? Let's look what it looks like. So we have a set of tracks, and I can change track. And when I select a specific track, it only highlights the pages which are in that track. I can search from the website, and I can structure in modules and in lectures. Yeah. How does that happen? Well, basically, we have a sidebar.gl here, so it's sidebar.gl, where we can specify each module. So here, like module 1, module 2, and so on. A tracks.gl, where we specify the tracks. And then if we look at the files at the lecture itself, so what the teachers would teach, let's take this one, for example. We see on top, we have a set of metadata. And now the only thing you need to do to build the website is to fill this metadata like properly. Arguably, if you don't fill it properly, it will scream at you a bit badly and could be a bit better, the error handling, fair enough. But yeah, so we specify what layout we want to use. And now if we want to say that this lecture belongs to module 1, we simply add in the list of tags module 1. If I want to move this to module 2, and maybe I want to change the order so that it doesn't collapse, so like the 4th lecture in module 2, let's save. Now this should refresh automatically. Where is it? Yep. And now we see that what file did I move? I forgot what I moved. Getting started. Oh, it's still here. Let's refresh. Yeah, that's what happens when you do live demos.
This is locally, right?
Yeah, this is locally. I'm running locally. There's also action to generate the website on CI. So there's an action so that when you push to GitHub, it builds automatically the website. And it also builds a preview on pull request so that you can check what it looks like before you merge. OK, oh, it's not moving. I'm not sure why, but it happened. Don't modify live. Modify before your lecture, not during your lecture. That's the lesson that I wanted to show you here. Yeah. So, yeah. So this was a very quick demo. I'm running out of time, but key take-home lessons. The template wants to make building the website as easy as possible, so you just build individual files as Markdown if you don't need code, as Pluto Notebook. In Pluto Notebook, you can actually set from the UI the metadata, and then it builds everything for you. There are a few improvements, and come to talk to me at the hackathon if you want to work with me on that. I'll do that. Like make the process a bit more robust, better error message, and better interactivity.
All right.
And that's all, folks. Thank you for listening.
Thank you. Do we have any questions? Questions for Luca?
I can save you maybe a bit of time if your question starts with can you. The answer is probably no at the moment, but feel free to ask. Yep.
Are there homework integrations planned for grading?
Yeah, so I repeating the question for the video. Is homework integration planned or already there? Yes, there is some homework integration already. So if you look, for example, here at the website, if you have some homework, you can simply put homework in the tag, and then it has a separate numbering and separate handling. So it handles homeworks. I'm planning also some integration with plutograder.gl, which I presented in December in Eindhoven. It's not integrated yet, but that's coming too. Yep.
Does the homework have an integrated way to give feedback?
So this plutograder.gl separate package, which is presented in December in Eindhoven, that's exactly to handle that. So it's this library to automatically grade homework and give feedback to the homework to the students. So that library handles exactly that. It should work in way because you can use Pluto Grader is very terminal based at the moment, so you could use that, but there's no integration to make it smoother into the template. So that's also a future development point.
All right, we have to keep moving forward, so thanks, Luca, again. Can we use this, or do you need the... Is it on the... Yeah. Is it the link? Yes.
Not the PDF though, right?
It's a PDF.
Nah, better the revisualize.
Oh.
But the link is there.
Yeah, okay.
So, if you go on that.
Oh, so next up we have a semi-local presenter from Delft.
Yes,
So
exactly.
Patrick, take it away.
See if I can get this in full screen. Yeah, there we go. All right. Thank you for having me again. Really good to be back at JuliaCon, and indeed locally this time, not a long trek from Delft. I'll be talking about what's new in trustworthy AI in Julia, and in particular this package ecosystem that I've termed TIJA. TIJA stands for trustworthy AI in Julia. And it's kind of a product of my PhD. That work has been going on for 3 years now. And I'm very excited to give an update today. So what is the ecosystem? At this point, we have a number of core packages. In 2022, I presented counterfactual explanations for the first time, and also Laplace Redux, which is for Bayesian deep learning. Last year, I presented conformal prediction, which is a package for predictive uncertainty quantification. And this year I'll also give a short presentation of joint energy models, which is a new package. We've also streamlined the ecosystem a bit to move a lot of functionality that was previously in core packages into various meta packages. Not all of them are super mature. So tire plotting, for example, does a bit more type piracy than I would like it to do. So if anyone is interested in visualization, this is a good place to contribute. And in terms of external packages from the Julia ecosystem that we target, it's mostly MLJ and related libraries, and then also Flux, which is one of the big deep learning libraries. So who's behind TIJA? Initially, it was really just myself as a PhD experimenting with Julia for the first time in 2021. But increasingly, there's more people getting involved, and I've just put a few contributors here to highlight some of their contributions. So Moji Farmamba is he used to work at ING. ING is a Dutch bank, and they sponsor my PhD. He's done a lot of contributions to conformal prediction, and then a lot of these other handles that you see here point to profiles of students at TU Delft who've been involved in this project as well. So if you're looking for contributors maybe for also your own work, these might be good people to reach out to. So let's get into the gist of it. What are use cases for Taija? Well, one primary use case is my own use case. I think researchers in AI and machine learning who are interested in explainability and uncertainty quantification could benefit from this ecosystem. Also practitioners, of course, working with conventional machine learning and deep learning models who are interested in understanding how do these models actually make their decisions. And then also, of course, Julia developers who want to contribute to a growing but still small ecosystem. So I thought I'd start off this year with a bit of research to just show you what can be done with these libraries. And also because that's what I'm supposed to do most of my time as a PhD. So to give you just a very short intro to what counterfactual explanations actually are, they are one approach to explainable machine learning. There's many more. I see we have Adrian Weller in the audience who has his own ecosystem on explainable AI using some different tools. Counterfactual explanations essentially work under the premise of simply perturbing the inputs into some supervised machine learning model to see what's necessary to change the output with some target output in mind usually. So one example that is commonly given is in the context of banking, personal banking, you might apply to ING for a loan, and ING Bank might use some machine learning model to estimate based on your financial data history if you're creditworthy or not. They feed this data through a black box, and then they say, well, unfortunately, you're not getting the loan. Then you have a right to an explanation, and counterfactual explanations offer a fairly intuitive and useful solution to this problem. And you can see that essentially in the classification context, what's happening in most of the time is that we're doing optimization, gradient descent in the feature space. So we're perturbing the inputs with some loss function in mind. I won't go into too much detail here, but we're trying to send individuals across the decision boundary from that negative outcome, application rejected, to the positive outcome, you're getting a loan. So one thing that you might have already seen now on the previous chart is that explanations in this context are not unique. So I can generate many counterfactuals. Is it not 30 minutes? Sorry. We can generate many counterfactuals that get us from A to B. So here we have an example for an image classifier, MNIST data, a famous data set. This is a very simple neural network that was trying to classify digits, and we're trying to understand what's necessary in the eyes of the model to go from a prediction of 9, which was the original correct prediction for this factual image here, to a 7. And you can see that the outcomes are very different. So these two, Wachter and Shoot, to me they look like adversarial examples. It's barely recognizable maybe that this has actually been turned, but the prediction has in fact been changed with high confidence. This simple neural network now predicts 7 instead of 9. And then on the right, we have a popular approach for generating plausible, realistic counterfactuals. So this one actually intuitively does look like a 7. And what these people use under the hood is a helper model. So they use a surrogate model, generative model, to understand what a 7 actually looks like, so to model the data generating process. And then they move in the latent space of that model, and finally it all looks good. So faced with this, we asked ourselves, okay, we have so many different ways to go from A to B. Which one should we use? Which is the explanation that we should trust? Do we just show the plausible one to people, and then it all looks like the model has learned reasonable representations of the data? how can we do that if these other adversarial examples are also valid explanations? So our goal was to come up with a technique to generate faithful counterfactuals that faithfully represent the quality of the model that we're trying to explain. And to do that, we kind of forced ourselves not to use any surrogate models. So no helper tools that could allow us to learn something about the data that the model has perhaps not learned. So we rely solely on the model, and we come up with this approach called ECHO, which stands for Energy Constrained Conformal Counterfactuals, which is a bit of a mouthful, but it essentially hints at the fact that we leverage ideas from conformal prediction and energy-based modeling. And I think the key chart here is figure 3. Here we show the same starting point again, so still this factual image 9, and we use ECHO to generate counterfactual explanations for different models. So we have in A here still the simple multi-layer perceptron, and then from A to D we gradually improve the model. We get a bit more rigorous during training about learning more about the data, learning plausible explanations for the data. So in D we actually have a model trained using this new package, joint energy models. And we can see that the quality of the counterfactuals gradually improves, and that reflects the underlying model, so not some helper tool that we've involved. So that was quite desirable. And by the way, everything you see here, all these results are generated in Julia and powered by Taija. Completely different context. Now we're in the context of conformal prediction, predictive uncertainty quantification. Imagine, back to the ING example, you work for ING and you're tasked with building a chatbot, a dialogue system that will make it easy for customers to log on to ING's website and quickly get help with maybe their exchange rate or their credit card got cancelled on a holiday. The chatbot needs to be able to essentially identify what the intent of the classifier is, of the client is, of the consumer. That's kind of the first task in many of these dialogue systems. So what you can do is you use some large language model as the backbone, and then you put a classifier head on top of that, and the classifier then tries to determine which intent the customer has. But if you know a little bit about classification models, they give you, in most cases, a vector of softmax outputs, so predicted probabilities for the different classes and intents. And it's very likely that especially if there's a big space of possible intents, that the most likely, so the highest softmax output, is not actually the right answer. So just giving the top one answer and moving on is likely to go wrong. So what you could do instead, and what people have done, is to show the customer the top k outcomes. So whatever k is, you can exogenously define that. It's not ideal, it's quite ad hoc. What you could do instead is to use conformal prediction to come up with a set of possible intents that fulfill certain coverage guarantees, where you can rest assured that the true test label is actually included in that set. And here's a simple application of that in Julia. This has led to another publication quite recently. I'll just leave this here. You can read more about it, both in this blog post and of course in the paper itself. And then, we have more research, one upcoming at ICML in next week, 2 weeks. And then various master's and bachelor's theses at TU Delft now, working with these packages, which makes me quite happy, because it's to a large extent the product of my PhD so far. And then now also more students are interested in contributing their own packages. So this one is very early stages, but essentially implementing some common techniques for adversarial training in Julia, all focused on flux models. Okay, finally getting to some actual software development. So in this talk, I won't provide too much of an introduction into the different packages, because that's happened at previous JuliaCons. If you're interested in a set of more accessible introductory slides, feel free to scan this QR code, which leads you to these slides that I presented earlier this year in London at the Alan Turing Institute. Yeah, I'll leave that up for a second. So instead, I'll just highlight a few recent developments. So what's new in counterfactual explanations? As I said earlier, we've done a lot of refactoring. Part of that involved moving functionality into these meta packages. Another thing another thing we did was to use package extensions, which were presented last year at JuliaCon. That has freed up a lot of loading times and just made the package a bit snappier. Also, a lot of performance improvements. I've started dabbling with profiling for the first time. And then we have a couple of new features, and we also published in JuliaCon proceedings. So this equation we had up earlier, what you need to know here is just that the majority of approaches in this world of counterfactual explanations relies on gradient descent. And they all kind of start from this general optimization problem. And then different papers, different authors have added their unique flavor to this equation to address certain desirable properties of explanations. And this made me think, well, if we have a library in Julia, shouldn't we make it possible for users and researchers to combine different ideas, since we all typically start from the same equation? And that's led to this, I would say it's still a little bit early stages, but we have a few nice macros here that make it easy to combine different penalties that people have proposed, different loss functions, to essentially easily combine different ideas that the literature has come up with and come up with unique flavors of counterfactual generators. So if you're interested, for example, in creating a diverse set of explanations, then you could use this penalty that was proposed in this paper by Motilal et al. A few years ago. If you're also interested in making sure that the explanations are very plausible, so they look realistic, then you could use this revise method that I showed you earlier, which searches counterfactuals in a latent space of a VAE. We also added more support for adding various systems in the ecosystem. So besides FluxJL, we have support now for models that are supported by the decision tree library. Also quite recently added neurotrees.jl. I think Jeremy is in the audience. There's a nice talk on this coming up tomorrow. Laplace Redux, which is one of our own packages, and also joint energy models. Another important part, especially for researchers, is to benchmark the final explanations. So as you will have seen or will have understood by now, there's many ways to get from A to B, and different counterfactuals address certain desirable qualities or properties in different ways. And the literature has come up with a large range of evaluation criteria. Quite a few of these are implemented, and it's very easy to evaluate counterfactuals using a very simple API call. You can also run large benchmarks across various models and data sets, and we also have support for parallelization through both multi-threading and multi-processing. And actually there's another talk on this topic if you're interested coming up also tomorrow. Now a quick look at Laplace Redux. So Laplace Redux is an approach to Bayesian deep learning that promises to be quite effortless and scalable. It relies on something called Laplace approximation, which is essentially a Gaussian approximation of both the prior and the posterior of the weights in a neural network. And it's been thought for years that this doesn't work, but then a few years ago some people realized this actually can work, and they produced a nice Python package in Torch. And essentially, Laplace Redux is a pure Julia implementation of that work. It was for a long time fairly early stages, also when I presented it at JuliaCon in 2022. But we had a couple of students working on this last year, and they added a ton of new features, such as the interface to MLJ, which is quite important, and also support for multi-class classification problems, as well as some more sophisticated and scalable approximations of the Hessian of the neural network. Again, I won't go into too much detail here, but essentially Laplace approximation needs that, so the second order derivatives of the weights of the neural network are used to approximate the posterior, the Bayesian posterior of the neural network. And yeah, that doesn't scale all too well if you actually use all of the weights, so you need some more sophisticated approximations that use less or need less information, less weights going into the final computations. And the students have added this and also added a nice blog post, which you will find on my website. Conformal prediction, since last year, since I presented, I personally haven't done much more development work on this. I've used it in our research, but Moji Famamba, he's added support for using conformal prediction in the context of time series prediction and also for quantile regression. So do check this out if you're interested in predictive uncertainty quantification. And then, as I mentioned a few times now, joint energy models is, I think, a very interesting approach to modeling, to supervised learning. So these models are really hybrid models that are tasked not only with learning to predict some output, but at the same time also acquire an understanding or at least some sort of, learn something about the input data. And I used this for our research and implemented a small package in Julia that works with both Flux and also MLJ through MLJ Flux. And you can see here an example. So we have some synthetic data. The contours show the predicted probabilities. So the model clearly learns to predict the classes, the output classes. And then these little stars that you can see here, they're generated from the model posterior using something called stochastic gradient Langevin dynamics. And they fairly accurately approximate the actual data, training data that we observe. So this model has learned something about both the outputs and the inputs. And that turns out to have these models have very nice properties with respect to trustworthiness, because we actually found in our work that if we generate these echo counterfactuals, so faithful counterfactuals for these models, they tend to look plausible because these hybrid models have learned something meaningful about the input data. Okay, a few final things. I think I have about 4 minutes. We have some ongoing work now through the Julia season of code. One is about bridging the gap between Bayesian and frequentist approaches to predictive uncertainty quantification. That's through Google Summer of Code. And then we have one on adding a causal angle to counterfactual explanations and algorithmic recourse. This has been really quite fun and is still ongoing, so hopefully we can share some results in the future. And I thought it might also be nice to show a student testimonial. So in general, the students I've worked with at TU Delft have been quite happy and enthusiastic about working with Julia. And here Rauno in particular said that programming in Julia has definitely helped him become a better programmer. That also goes for me actually. And that whenever they had questions, they were met by friendly responses by the broader community. So I think that's a good result in itself. And finally, just one more slide. If you're interested in any of this work, if you're interested in using it or contributing, do feel free to reach out, come approach me at the conference, or find us on Slack or GitHub organization. I'll leave this here. The link should point you to my website where you find all of this as well. And with all of that, thank you very much for your attention, and feel free to ask any questions.
Thank you. So we've got plenty of time for questions. Do we have any?
All right, so how does the chatbot actually work? How does the intent classification? I came in slightly late.
Let me go to the slide again.
So if you already answered that, I apologize.
No worries. So are you familiar with the Fast AI interface?
Yeah.
So they, and I think metal.jl as well, they have a nice way of framing this, of calling the backbone, the bigger model in the background that is essentially used in this context to take the speech, the text that's coming in, and embed it. And then you put a classifier head on top that you can fine tune for some classification task.
So does that mean you have a language model running internally in Julia where you can do the backbone, or are you bolting this on somewhere else?
This is a fairly small model. It's like a Roberta model that I pulled from Hugging Face. So
okay,
it's
gotcha.
not really a large language model in today's terms, I guess.
Right, but it's good enough for classification.
Yeah. For this, it works fair enough. Yeah. Well
Okay.
enough.
Cool. Thank you for walking me through that. Appreciate it.
Just coming to the basic, so the event or the workshop was about trustfully, and you pointed out Taija. So other areas in AI are not trustfully? That's my question.
Very fair question. Well, I think this depends a lot on how optimistic you are about AI in general, I guess. But there are a lot of vulnerabilities, instabilities in modern, especially deep learning architectures that we're very aware of. Adversarial attacks is one of those. But also the fact that we simply do not understand how these models make their decisions. Once they're big enough, there's just too many parameters to look in there and look at. There's no linear coefficients that we can reach to easily interpret these models. So I find it very hard to trust that type of model in a safety critical situations. Those are often mentioned, but also in more everyday life type of situations. So I mentioned the loan application. If you have no means to explain why the model decided that you're not creditworthy, that's problematic, and I find it hard to trust a model like that. This doesn't mean that Taija, because we use that name, provides the answer to all of these questions. There's many different approaches to explainable AI, but my PhD is focused on these particular topics, and we try to think critically about these AI models and that way gain some more trust in these black boxes.
No, thank you for the answer, but I'm thinking now in my company that even they are block ChatGPT for the employees, and we have Copilot open for us. So I was thinking okay, then perhaps in the future we will go to Taija, because the vulnerability companies are thinking about that already and are blocking certain areas. So what is your experience that?
I mean, I'd love to chat to you more about it, but I will say that it is still a fairly small ecosystem that does very specific things. But yeah, we're very ambitious to develop it further, and any type of practical application, any problem that people might face, do feel free to approach me and we can chat more about it.
Hello, I wonder regarding explainability thing and trustworthy, basically the main thing that you do is you perturb certain kind of parameters and then find out something. But usually you are dealing with 5 parameters, and their interaction can be nonlinear. So when you perturb something, my question is that knowing what parameters to perturb does not really do the explainability, right? So we always have the thinking that, I know this parameter is the one that that produces this kind of thing. But that does that really provide explainability?
Yeah, so this is going into basically the depth of what all this research area is about, and as I hinted at earlier, people have come up with different things that they think are desirable about explanations. So some argue that explanations should always be causal, and in fact, one of the Google Summer of Code projects that we have is working on a causal implementation. I find that appealing, but that approach relies typically on assuming that there is some causal knowledge in the background. So that doesn't always apply. They all come, I guess the short answer to your question is, in my mind, all of these counterfactuals here that you see on this image, they're all in some way explanatory about the behavior of the project, of the model. They tell us something about the model. And finding the right explanation that meets all those criteria is quite difficult, and I'm not sure it's possible.
Is there a danger that this kind of perturbation, which is very localized in something, can lead you to a wrong conclusion? Or so how confident are you that when you perturb something, is you have this kind of explainability, you have this certain kind of certainty that your explanation is correct? It can be just a rhetorical question. Thank you.
Yeah. Well, one thing that's nice about counterfactuals is because they work directly with the model, validity is automatically defined. The explanation, as soon as it switches the label in the target direction, that's the label that's predicted by the model. So correctness is kind of given by construction. Yeah, I'm not sure that directly answers the question, but I'm also happy to chat more afterwards.
I'm not sure about that, if that's the approach that you take, but like rather than creating a chatbot, which I think it's a very good idea, can't we just give a range of coefficients to an algorithm and repeat the training of the neural network until repeating the training of the neural network by giving it different randomized parameters to the neural network downstairs, and just reassign the model neuron numbers in every trial if the coefficients aren't in the intended range? Like, can we just do that as a option, like, which we will also have a clear range and clear values, that rather than just saying it's not what I want, so that we can just say, no, I wanted 0.25, but the model gave me 0.2. So
I think let's take this question online, because I think offline, because we need to move on. But let's chat now.
So thank you so much, Patrick.
Thank you.
And let's give him a round of applause again. Chiante?
Yes.
Okay. Can you? You're gonna get mic'd up again. Okay. Connect there. So now we have Chiante Fernandez, PhD student at UCLA. So welcome and take it away.
Hello? Cool. All right, thanks. I'm excited to be here at JuliaCon. This is a really unique and awesome opportunity. Many people in my field haven't moved to using Julia yet, so this is a really nice way to meet people in different areas. Cool. Yeah, like we just mentioned, I'm a PhD student. I'm currently in my 4th year. I work in an area called neuroeconomics, which intersects with experimental economics, cognitive neuroscience, and cognitive psychology. Yeah. I just want and I'm going to tell you about our Julia package here. I just want to give a shout out to our primary maintainer. He really is when I joined the team, have a lot of thanks for Chris. So just want to give him a shout out here. And this QR code takes you to our repo. Right, so this crowd is quite broad, so I just want to give a kind of little broad introduction of the things I'm interested in. I'm interested in this class of models, this class of generative models called cognitive models, and really what they do are just specifying parameters that have particular psychological interpretations that we use to describe behavioral data, primarily amongst various organisms. And I'm interested in humans a lot of the time. A question I might work on in decision making is how people evaluate these options, right? So how you choose between food options. And then I'm interested in the various relevant processes that are at work while you evaluate these goods. And the output of that would be something like the speed to which you would respond when choosing these options. And indeed, in my area, in cognitive neuroscience, there's this general class of decision-making models that are attempt to capture the distributions for response times amongst some set of alternatives. And we see that as really the gold standard. So just to give you some intuition about what these models do, they tend to look something like this, where you start with some predisposition or some set starting point, right? They could be parameterized here as k, and then you're going to sample some, this is an abstraction, right, of evidence over time, and you might call it nu. And that's to some bound, right? And that could be alpha here. And we also have to account for time to just encode stimuli, as well as to execute some motor output. So that can be characterized by tau here. Additionally, all options, or at least in this specification here, are going to have some kind of evidence. So there might be competing evidence here. And you can see how each one of these parameters have various dissociable components related to the psychological processes underlying the decision. And then these are then captured in these distributions. And they're used quite pervasively throughout the literature. They're used to study humans, of course, as I mentioned, and monkeys, mice, and even zebrafish in some applications. And fundamentally, many of these models are just stochastic processes, and we're interested in that first hitting point, right? This time to some bound, right? And though they're not limited to the continuous formulation of the stochastic process. As I mentioned, though, there's a wide range of these, and they vary as a function of how much evidence might be competing with one another, as well as the type of response you might be interested in, which could be discrete or it could be something more continuous. And they also try to attempt to characterize different other cognitive processes, such as how attention might change or vary the drift as a function of time. And out of the box, people might go and simulate these SDEs. If you're in my area, you might simulate them using something like Euler's method, or you might have closed form solutions for the probability density functions, for the first hitting time, or the stochastic process. But all of that can be quite complex or complicated for people in cognitive psychology. And so a lot of work has been done to develop interfaces for simulating from these classes of models. And yet there's yet to be any interfaces for simulating from these models in Julia. And so that's what sequential sampling models.jl aims to do. It's to provide this one-stop shop, really, for simulating from these models. And really what it builds on is it builds on the distribution.jl, and it creates an abstract type to which we develop these set of constructors to where we can sample from using distribution.jl methods. And what's nice about that is that you can not only use a sample from them, but you can, if you have closed form solutions for the likelihoods, you can also incorporate it with Turing, which is of interest to people in my field because we like to do parameter estimation for these generative models. So I'm just going to give you an example then of using the package. Right? So here it's on the registry, so you can just use it outside the box. And here I'm just defining a model. So this is a constructor for one of those popular models in my area, and then it'll output a set, and I'll show this little table that gives you the parameters and the fixed values you defined. And then you can just call methods like this. So you can, and it will output the choice and response times from that generative fixed set of parameters. We also developed some plotting functions that give you these nice response time distributions for the choice for each of the n alternatives, right? As well as we'll give you some of the simulated traces for some set of simulations from that generative model. It also works with Turing. So here I'm just showing a little example using the model macro, right, to specify, in this case, the LBA, and then just sample it and show you can get recovery for the parameters for this model. Some developments that we're interested in continuing to expand the suite of models available. So like I showed before, there's a large range of these models. So let us know if you want one included. That's not there yet. Also, as I kind of alluded to, there are some instances where we don't have closed form likelihoods. And so we would like to still sample from these in an efficient manner using a probabilistic programming language like Turing. So one solution might be to use some of these amortized inference techniques, which could be built with Flux and then still sampled with Turing. So if you're interested or an expert in Flux, come talk to me. Also, because this package is built for substantive researchers in my area, right? It would be nice if it's intuitive and easy to use. So we'd like to create also build on Turing GLM so that you can sample from these models using some kind of specification like this, where you can have your parameters as a function of some set of conditions, just making it easier for the user. So thanks again, and here's a link to the repo. Go ahead and check it out. Yeah, appreciate it.
Do we have any question from the audience? Here.
Hi. Have you considered using the SciML, what's it called, interface for example, stochastic solving in order to do these simulations? I don't know if that's even a possibility, but I would imagine so, right? Because it's pretty much optimized for those kind of problems.
No, so many of the constructors that I showed, they do have analytical solutions for the PDF, so we don't have to do that in those cases. In the instance that I showcased that the Euler's method for the SDE, it was just kind of to show for in instances we haven't looked into SciML yet.
Okay.
Yeah.
Thanks for the talk, Keontae. I had a question. I don't know if this really applies to your work, but I've been thinking a lot about the running interface discussion that's kind of been going through the conference a bit. And I guess this is a really interesting idea where you've got all of these different sequential sampling models. Was that right?
Mm-hmm.
Have you thought about, as you're extending them and adding more, about kind of abstracting that problem, or have you already made some work towards that?
Yeah, the workhorse here really is the set of abstract types that we have defined here that we use to define the constructors. I haven't thought I guess, in the same way about how they might be thinking about interfaces, but I think there's a talk later today that I hope to go to. Yeah. Thanks.
All right, thanks again. We have our last talk from this morning session from Caleb. Caleb is a software engineer implementing one of the most needed features in the REPL of V-mode. So, three and one left. Three and one left. All right.
Hi, everybody. My name is Caleb Allen. Today I'll be talking about the virus that is VI, that is infecting most software out there, and its progression toward the Julia runtime and the Julia REPL. I really like VI. and Vim and all of its descendants. I think it's a great computer program. It was invented by Bill Joy in 1979, released as part of the first or second Unix distribution out of Berkeley. VI allegedly comes from the visual part of it as the first visual editor that took a step beyond just line editing from the terminal. It has a lot of great features. It works with many languages. It has macros. I love macros. You can search with regular expressions pretty efficiently. And it can also operate on very large files that many other editors would struggle with by using buffers. I also think that Julia is a great computer program, hence, being at JuliaCon. And it has a lot of very nice features that I think merit investigation for people who use Vim. It was launched in 2012. It works with many programming languages, including C and Python. It has macros. It has regular expressions. And it can operate on very large files with buffers. So, on first look, for a Vim user, it's kind of got a lot of some features in common with Vim, with Julia, I'm sorry. But we're kind of in this predicament as VI users. On the one hand, you have this powerful, dynamic, performant, expressive programming language that is able to tackle problems that are either difficult or impossible in other programming languages. On the other hand, it's not VI, and it's not a VI descendant. So how do we just go about allowing ourselves permission to use this program? Should we compromise? Should we decide that some non-VI programs are worth using? And maybe have we become a little enthusiastic about using Vim and trying to move and transform every other program we use into Vim with the browser, with editors, you name it, there's often a Vim implementation of it. And even Bill Joy, the author, says VI was written for a world that doesn't exist anymore unless you decide to get a satellite phone. So the author himself has kind of insulted it, really. But I think we all know that once something's been unleashed into the world, it can't be recontained. VI will not be contained. VI finds a way. So last year I presented vimbindings.jl, which it's a pure Julia package that's available now. It emulates many of the features of Vim directly in the Julia REPL. And it gets the job done. It moves a Vim user from not being able to use Julia at all to maybe being able to use Julia with reservations. But it's not. It's a partial implementation, and it's not very configurable. This is what I see as the Julia community, the innocent REPL users, and the Vim bindings package being unleashed. Just the start of what's to come. So, changing directions a little bit, I want to take a look at a different ecosystem. VS Code NeoVim, which for those who are unaware is it's an extension for the VS Code editor, which implements a Vim mode by essentially outsourcing all of the Vim work to a running instance of NeoVim and wiring up API calls, which allows the package maintainer, the extension maintainer, the freedom of not having to implement every single feature of Vim, right? So it also makes it configurable, essentially puts the Vim instance under the editor. So in this scenario, I see Dr. Frankenstein as an enthusiastic Vim user who's using VS Code, which is the body of the monster, but the brains of the monster is running on the NeoVim API. And I have been working on a prototype that does this for the Julia REPL, and gotten some progress. There's still work to be done, but effectively, this outlines what that looks like. You have the Julia REPL running on the one hand, a remote procedure channel talking to a NeoVim instance, and then communicating the text changes, the key strikes, and so forth. The documentation for this is at that URL. So the reason I'm presenting is that I'd like to solicit feedback from users. There's a lot of questions that are not technical, but are design questions. Is a NeoVim feature, is somebody who would, among those questions are, do we restrict what NeoVim features are enabled? Like marks, plugins, how do these interact with the REPL? It doesn't, it's very unclear. Do we use a local NeoVim instance or use the package manager? Do we bring this into Vim bindings package or create a new package? Effectively, come talk to me afterwards if you have any thoughts about this. I'd love to discuss. After all, for many users, it is a Unix system, and I think we want to keep it that way, no matter where we are computing. Thank you.
All right. Thank you, Caleb. And do we have any questions here?
So I guess I'm curious, are you interested in embedding NeoVim within Julia or embedding Julia within like a dedicated like NeoVim pane?
The former.
Okay.
Embedding is effectively yes. So,
okay,
starting up a NeoVim instance and binding the key bindings.
Okay.
But this is exactly the conversation that I'm looking for. Is how do we want to do something like this?
Okay.
The most important question. Once I have Vim bindings, how do I exit the REPL?
That's that's the genius of this virus. Is once it's in there, you can never ever get it out.
That's why I'm still using Vim.
Yeah.
All right, if we don't have any questions, let's thank our speaker again. And I'd like to remind you that after this, we have our second keynote of the day. So head to the main stage if you want to attend to that. And we have a short break of 10 minutes after this. So. until they show up.
This is not your first talk, but
no.
I'm not supposed to be the monitor.
Okay.
But until they show up, your 30-minute talk, right?
Yeah.
Okay.
Oh.
I will do a quick introduction.
Great.
5 minutes.
1 minute.
1 minute.
Great. Thank you.
That's the sign, yeah, as soon as he finishes that. Okay. We're going to, so this is room 3.2, if everyone is in the right place. We're going to be having a talk on diffieqgpu.jl with Oscar Smith. So I will hand it off to you.
So yeah, as previously mentioned, I'm Oscar. I work for Julia Hub. Pretty much all of the work in this talk was done by Uktarsh, who's at Julia Lab MIT CSAIL. But due to some travel issues, he's not able to be here today, and so I'm presenting this. First of all, why do we want GPUs? First of all, actually, why aren't my slides switching properly? Okay, so this is your differential equation, or ordinary differential equation, initial value problem. So you have f of upt equals du dt, and you have a time interval, and you have an initial condition. And we want to solve these, and we like to solve things in parallel where we can, but unfortunately for an initial value problem, it's a fundamentally fairly serial task, because to know the time at t, you need to know the time at t minus delta t first, and so you can't parallelize that easily. However, there's lots of situations in which you want to solve a bunch of problems. So you want to say, if I vary my parameters a little bit for process variation, how will it look like if I'm solving 10,000 differential equations that are all slightly modified at the same time? Or maybe I have a bunch of different dynamics I want to explore, and so therefore we have a lot of equations. And in that case, you can actually just essentially run all of your equations at the same time on a GPU. There's a lot of details to this to make it work properly. But so the other case that we will not be talking about today is sometimes you're solving like a big PDE. If you're solving a giant PDE, you can make your linear operations be on the GPU, and then it's easy. You don't need anything special from the SciML land for that, other than linear solve and nonlinear solve and all the other special things we do for that. But you don't need something special for the GPU or for the differential equation side. But if you have many ones, you do actually need, it turns out, some specialized things, because the naive way of parallelizing to a GPU doesn't work especially well, which we'll see. So yeah, the naive way is array-based data parallelism. So that's where you just make your U not be a Q array, and you make your P a Q array, and your T and your all of your problems a Q array, and then you solve all your problems like that, and then all of your time stepping still on the CPU. And as we'll see, this has some significant overheads. But we're in Julia, and we can do some fancy things instead of that. And this is where we get into custom kernel generation. So with custom kernels, what we're going to do is we're going to generate the method for doing all of the ODE solver on the GPU, and this will dramatically lower the overhead, as we'll see later. But first, there's a number of different packages outside of the Julia land for doing differential equations with GPUs. There's MPGOS, which is C++ and explicit solvers only. There's Diffrax and PyTorch, which are both Python-based tools. The big downside of both of these generally is that they mostly only support the array-based methods because they're coming from a deep learning-y side of things where you're doing big matrix multiplies and therefore you don't need some of the fancier stuff. And then there's Janelle Soda, which is a GPU version of the C or Fortran, I forget which, I think C, LSODA solver, which is a stiff solver. And yeah, so given that all of those libraries exist, why do we need to write DiffyQ GPU ourselves, and why was previous software not perfect? So we have our FFUPT, and you generally, like, just making your right-hand side run on the GPU is not trivial. You need to be in a relatively restricted subset. If any of you have worked with GPUs before, you'll know about the scalar indexing errors that you can sometimes get when you're trying to run things. But to write to make it easy to write high-performance GPU code for this sort of case, you basically need to use something like SPMD, so many data single program. But yeah, so the traditional approaches generally don't get the performance you want, and so Ensemble GPU Array is the DiffyQ GPU version of the previous approaches, basically. So you just take a big array of things and you solve it on the GPU, and then you come back to the CPU for your time stepping. But the main innovation of DiffyQ GPU is Ensemble GPU kernel, which is where you do the kernel generation custom. So yeah, this is just going through what it looks like. So rather than having your single U and P, you just put them into a big matrix, and then yeah, as you can see, the solver ends up looking very similar to what it would be regularly. So you start here, and then your function evaluations and Jacobians are done on the GPU. Your factorizations are done on the GPU, but then you do your step synchronization on the CPU, and then the problem is that this can end up being a bottleneck, or this orange here can all be a bottleneck because that all ends up on the CPU. And launching GPU kernels takes a couple microseconds, and getting data back also takes a couple microseconds, so that can be fairly slow. And yeah, GPUs have the best success when you're doing operations that scale with O of n cubed, or n squared is also pretty decent, but because there the computation is the dominant cost as opposed to data movement, and GPUs are essentially what you get if you take a computer and you throw out most of the complexity that makes data movement and look up fast, and just stick as much computation on them as possible. So if you have highly computation bottlenecked code, GPUs are great. But the ODE case, you're largely dealing with O of n code, or O of n algorithms. So the data is about the same size as the computation, which makes the GPUs generally be pretty memory bandwidth or bottlenecked. And then the other problem is that because you have synchronization at time stepping, if you have different problems that take a different amount of time, you run into the issue where the longest running one will bottleneck all of the others that finish first. This won't be a problem for some systems, it will be a problem for others. It depends largely on how deterministic your ODEs that you're solving are in terms of how long they take. And so the new approach is that we create a kernel that has the Runge-Kutta steps in it. And this approach means that you only launch a single kernel for the entire solve pipeline of all of the problems on the GPU. And this is completely static. And each thread is giving you a separate ODE, each GPU kernel is doing a separate ODE, and this means that you get a much better scaling in some cases because you aren't bottlenecked on all of the solvers, all of the time steps having to go back and forth between the GPU and CPU. And so the solver support so far, and apologies if this is outdated, Chris Rokakis in the back will tell me, hopefully, if it is outdated, but we support Seat 5, Vern 7, Vern 9 for non-stiff solvers, which are generally the best in terms of medium to high accuracy, so rel tall, abs tall of like 1e-6 to 1e-9 or 10 or so. And then for stiff ODEs, we have the Rosenbrock W methods, Rosenbrock 2.3, Rodas 4, Rodas 5P. Rosenbrock 2.3 is the best for ODEs with loose tolerances, so 1e-3 or so. Rodas 5P is generally my favorite ODE solver. It is really good in a lot of cases, DAEs in mass matrix form, ODEs with relatively high tolerances. And then we also have 2 SDE solvers. I do not know much about SDEs, but we support them on the GPU and in the kernel mode. And then there's also the Caverno solvers, and I don't know what they do. I've not used them. And so yeah, as you can see here, with the Ensemble GPU kernel approach, we get, there's no synchronization loop. So yeah, you don't have to go back to the back to the CPU every time step. And this is why it will be much faster. Because yeah, you generate, so yeah, the way that these work is you start with your symbolic representation because symbolics is a very good way of optimizing your problem. So we can do this from Catalyst, Modeling Toolkit. There's another bunch of others. So I don't know if we've ever tried Ferrite, but presumably Ferrite might also work here. And then from there, we generate the ODE problem. And because we have symbolic frameworks at the top of this pipeline, we can make sure that we only generate GPU-compatible code. And then when you call the solve of the problem with the GPU, we will generate a kernel, go through kernel abstractions, which does the Julia compiler with a bunch of specialized things to make it not generate CPU code, but instead generate GPU code. And then that produces optimized LLVM-IR in the same way that a Julia compiler does, because LLVM can also compile for GPUs as well as CPUs. And then that gives you a GPU native device code. So unlike a lot of other GPU frameworks, we don't generate C++ or C. We actually go straight to GPU assembly, which can be a significant optimization benefit. And then also for AMD and Apple, the process is fairly similar, but it gets a little bit different because of some technical details to do with what the GPU stack looks like for those pipelines currently. And so now there's a live demo, and I wasn't sure if this was going to work because I'd heard rumors of SSH being bad, but we seem to have it working. So let's see. Where did that go? Okay, there we are. Where? Okay, cool. So, yes, good call, thank you. How's this? Wait, here we go. So yeah, we can load our packages. Eventually. Time to first plot's not too bad on this. And so here we have just a simple Lorentz problem. It's the classic demonstrator. It's a chaotic system. It's one of the simplest chaotic systems that exists. And so we are going to make a static vector for our initial condition, and then we're solving this on a 10-unit time span. We have our parameters, which are just the traditional Lorentz parameters, and then we can define our problem. This should all be fairly standard to any of you who've used ordinary differential equations before. So where this starts to get a little different from what you might have seen is we're going to define a prob func and then a Monte Carlo problem. And so, wait, first, why is this here? And what? Oh, because I never defined my prob. Yeah, what? Okay. Live coding is hard. And then, yeah, so this is using okay. Oh yeah, I know what happened here. There we go. So this is using ensemble problems, which is an interface in ordinary DiffEq to let you solve many problems where you give it a prob func that tells you how to generate new problems. So it lets you very easily make very customized ensembles with lots of different parameters. And so now this system, so if we run LSCPU, you can see that we're on a Zen 7 or Zen 4 CPU, so AMD EPYC 9000 series, 64 cores, hyperthreading off. And if we do NVIDIA SMI, you'll see that we have a Tesla V100, so pretty high-end CPU, pretty high-end GPU, and we can now show. Why does it do that? I think I might need to escape from this presentation. That might make things work better. Yeah, here we are. So we can run the problem on CPU with ensemble threads. So this is running it in a multi-threaded mode. There's also ensemble distributed for multi-node computation. So this is just our CPU baseline. Apologies for the time, it is compiling. But yeah, as you can see, this takes 14.5 milliseconds, which for solving 10,000 trajectories, that's pretty good. And then if we just run it with a GPU, and this is ensemble GPU array, so this is the one that we expect to be higher overhead. I probably should have started running that before I was talking. But this is also going to take a while to compile. And what we'll see afterwards is that instead of being 14 milliseconds, it will be something closer to 150 milliseconds. So here, like, GPUs are supposed to be fast. What's happening? Also, why is it taking so long to compile? But yeah, as you can see, this was 150 milliseconds. So we used a fancy GPU that we spent $10,000 on, and we're 10 times slower. What's going on here? And the answer is, especially for this example with Lorentz, because it's a chaotic system, you run into the problem where it does get very bottlenecked because all the time steps are trying to communicate with each other, and it has to take a lot of time steps, and so you end up with a lot of overhead. But so instead, if we do the GPU seat5, which is the kernel method, you can see that we're 8.5 milliseconds, and that's twice as fast as the CPU. And so that's a pretty reasonable speed up. I forget. Yeah, so this is float 32, so we have an expensive CPU. We have a expensive but not the newest GPU. This is a 4-year-old GPU, I think. So if we had an A100 in here, it would probably be 4 or 5 times faster. But yeah, even just with a expensive but not top-of-the-line GPU, we're getting better performance than one of the best CPUs that you can get. And so now, exiting this, I'll bring it back in case we have questions about this later. Cool. And then going back to the presentation. Yeah. This, by the way, was me putting all the code here because I did not trust that SSH was going to work because I'd heard bad rumors about it. But we actually have a live demo. And so as you can see in these benchmarks, we're faster than CPUs for most tolerances with the kernels. And this is a work precision diagram. If you haven't seen one before, the x-axis, this isn't a work precision diagram. The x-axis is number of trajectories, y-axis is time. So if you have enough trajectories, so towards the right, you can see that Ensemble GPU kernel is a lot faster than Ensemble GPU array always, and with more than about 1,000 trajectories, it can be noticeably faster than CPU. And so we are also not advancing slides. And yeah, so benchmarking versus the other GPU solvers from the other packages we were mentioning before, you can see that there's 100x speed up over tools like PyTorch and JAX. And this is because they are using more of the Ensemble GPU method, which has inherently higher algorithmic complexity and overhead. Yeah, so all of the array-based parallelism methods are slow, all the kernel-based methods are fast. And so as you can see also, I can't demo this because this is a Dell rather than a MacBook, but this runs on Metal, so if you have a MacBook, you can get DiffyQ GPU running on that. If you have an AMD GPU, you can run on that. If you have an Intel GPU Y, but you can run on that also. And you get roughly the performance that you'd expect based on the comparable flops. Yeah, and these are just the GPUs that those benchmarks were on. And yeah, Ensemble systems and SciML are in general ready for multi-GPU and multi-paradigm systems and HPC. And yeah, as a bonus, if you do some fancy stuff, you can get this running on WebAssembly. If you try doing things that are too complex, it will probably break, though. And I think that is ready for questions, pretty much. And then also after a couple questions, I'm going to show a custom slide that Chris told me I have to show you guys with like 2-hour warning. So yeah.
Okay. So is there any questions? I'm going to be moving around the mic for you guys.
Thanks. It was a very impressive talk. Have a question whether this kernel dispatch would also work for stochastic differential equations. I assume here it was only parallelization over the initial conditions and the parameters.
Yes, it can. We have 2 SDE solvers implemented, and it is possible to implement more of them. And I do not believe we've done so yet.
Yeah, and so if you use the kernel-based SD solver, so there's the Euler-Maruyama method, but then there's also a method that is second weak order, because if you want to do ensembles, you probably want weak order, right? So there's a second weak order method on there as well. And if your prob func is just run the same function all over and over, then it will basically parallelize that ensemble where it's taking different Brownian motions for the solves. You can also mix, randomness in the parameters and randomness in the Brownian motion and randomness in the initial condition. But I mean, yeah, the case where you just say one set of initial conditions, one set of parameters, and I want to check the property of the stochastic differential equation, you just directly use the kernel GPU method where you just say prob func equals, just use the same problem every single time, and it will give you that Monte Carlo solution, right? And yeah, and you'll get some pretty nice speed ups with that over the threading methods. Yeah.
Not really a question, but a bit of cheek from me. All Raven problems are dominated by data movement between the CPU and GPU. For AMD MI300A, the CPU cores share 128 gigs of HBM with the GPU. And people have seen huge speed ups in, for instance, the OpenFOAM code. I don't know if you've had a chance to try them. Probably be very interesting to try that. And to be honest, then NVIDIA Grace Hopper does something very similar.
Yeah. I have not had the chance to experiment much with those, but they are interesting possibilities for generation. Give it to Chris.
Yeah. Well, I think that the main answer just is by making the number of data movements and synchronizations essentially 0, because you just run the entire solve on the GPU,
that's good no matter what architecture you're on, right?
Yeah.
So yeah, the AMD GPUs, they tend to have like a lower overhead because of synchronization, but it still dominates until you have enough trajectories, right? In fact, if you go back to the plots, you can actually kind of see what happens to these plots. If you look at these, right, they're almost flat for a while, and then they have that kink in there. That's basically the spot where you've actually filled the GPU up enough, and so that way, until then, the entire GPU run is the same amount of computation. You just haven't filled the GPU up, right? And so for a lot of cases where people are actually using, I want to do 10,000 solves on a GPU, we're actually not even filling the GPU yet. So trying to make sure like there's no data movements at all or anything is actually really essential, because we're just like, we need the biggest GPU the kernel call that we can, because you don't really have that much computation until, if you have 1 million ODE solves that you're putting onto there, yeah, you're filling the GPU. But a lot of people's cases are like ensembles of 10,000 things, and we have to really make sure that we use a GPU well in order for that to matter.
And there's also probably some work in the future on better ODE solver methods for GPUs that use more stages to get you extra parallelism. Oops.
Okay. Yeah, I was just curious if this type of parallelism can handle event callbacks, or if that would kind of kill the performance.
Chris is giving a thumbs up, which is surprising to me. I would have thought it wouldn't work.
Open up the paper. We have examples of continuous events and discrete events in there. Yeah.
Oh, cool.
The GPU is able to. You need to make sure you're very careful with how you write that code, because you have to make sure that it's completely type stable and everything, so that way we can generate a static kernel for it. But yeah, things like bouncing ball and stuff. Those are examples that we use to show that the kernel generator is compatible with the event handling system.
Question back here.
One question regarding the array-based methods. With recent CUDA releases, NVIDIA has introduced kind of these graph-based kernel launches, right? Which don't require your CPU to actually launch the kernel, but instead you can have the controllers on the GPU launch the kernels for you, with much lower kernel launch overhead. Is this something that would make sense to use here, or is it?
It probably would make sense, but it still won't be as good as just doing it all in a single kernel. So it's one where, if we hadn't gone through the work of inventing this, yes, it would be a great thing to use. But we have the good thing. Just use the good thing.
Can you train neural ODEs with this?
Yeah.
Easy question.
Chris wants to give a more than one word answer, but the answer is yes.
So go to the other paper that we just showed. So the next thing is okay, we have ODE solvers that we put on the GPU, but could you also embed nonlinear optimization on the GPU as well if you can do a kernel method?
Yes.
Yes. Well, could you then do a global optimization where you put a GPU, where you build a kernel that has an ODE solve and a nonlinear optimization per GPU core, and then do multi-start optimization from different points in trajectory space, and then you just take whatever the global optimization solution is? The answer is yes. And could you do that with a neural network inside of an ODE, inside of the optimization, all on per GPU core? The answer is yes, and this paper is the example of it. And so you go check out the paper there, and then there is a library, psogpu.jl, or it's gpupso.jl. I forget which way we did it around. So basically, all of these tools that we have for GPU kernel generation, we've extended it to the optimization tools. It's not all released now, but all the packages are out there for you to use. And the reason why it's not all released yet is because we're formalizing what simple optimization.jl will look like. Again, if you saw the Stata SciML talk, the next thing that we're doing is a lot of making sure optimization.jl is as mature as these other tools, and making sure that we do the right testing on all the optimization tools, so that way they don't break on GPU, is part of this maturization of optimization.
I feel like yes was the short enough version of that answer.
Okay, we have time for one more question, and if the next speaker wants to, you can start getting set up. Or if the next speaker needs to find his partner, he can come on up. One more question?
Just also another question on the behavior of this ensemble problem. If, for certain trajectories it fails to converge, like it would be fully.
So the way that this the interface generally works is that with an ensemble problem, even if the whole thing doesn't converge, you'll still get answers for the parts that do converge. I'm not sure with the ensemble GPU array whether that will have a short-circuiting behavior, but I don't think it does. It doesn't. Chris is shaking his head, so no. Yeah, you get answers for the parts that we have answers for, and you get failures with ret codes for the ones that don't.
Yeah. So let's give a good hand to Oscar for his talk. And we'll get ready for the next one in just a second.
This on because
yes, this is the man to talk to for.
Perfect.
Is this on? Yeah.
All right. So if anyone saw the last talk and thought gradients, those look really interesting. Everyone keeps telling me that Julia has this auto differentiation thing. How does that work? My understanding is this is the talk that will explain how to get started with auto differentiation in Julia.
Exactly. So we are Guillaume Dalle and Adrian Hill, and we're going to talk about gradients and give you a little tour of the automatic differentiation ecosystem in Julia. So we're going to start with a very, large, high-level overview of automatic differentiation, what it is.
Mention where we can find the slides, maybe.
Oh yes. So if you haven't scanned the QR code yet, then I will give you a couple of seconds to do so.
Yeah. And the link, is it on? The link is also on the pre-talks page for the talk, for the slides.
All right. So we're going to tell you what AD is, the state of the Julia ecosystem, and then move on to a high-level overview of how it works, how to use AD in Julia, what sort of common pitfalls are and how to avoid them. And we're going to end on a high note by showing you a project we've been working on over the past month, which is differentiationinterface.jl. All right, so let's get started. So maybe the most high-level idea is to talk about what a derivative is, and the most simple mental picture you can have is that it's a linear approximation of a function around a given point. And why do we need this? Derivatives and gradient-based optimization are essential optimization, and especially in machine learning and deep learning. And when we talk about functions, I should emphasize that more specifically, we're talking about functions expressed as programs. And in an ideal scenario, you wouldn't even need to do that much to compute derivatives. With automatic differentiation, you should ideally get them automatically. All right, so when we talk about the state of AD, we want to first emphasize that there's three different types of people who use AD. So first of all, we have package users who want to differentiate through functions that are exported by packages. Then we have package developers who write those functions and who want to make them differentiable. And finally, we have backend developers who make these awesome packages, these awesome AD backends that we use. All right, so let's get started with the user experience. And I would like to sort of motivate this by comparing it to the state in Python. So let's say we are a user and we want to use, we need to make use of two packages, a package foo and a package bar. So the way you would do this in Python is that you would first pick a framework, which is basically a domain-specific language. So the big ones are PyTorch, TensorFlow, and JAX. And once I've selected my sort of framework, then I hope that my packages are implemented in this framework and I can use them. So in some sort, users of these packages have a sort of three-language problem going on. So within Python, they use a framework which in itself is written in a sort of third language again.
And sort of the crux to this is that packages need to be rewritten for each of these frameworks. But once you're in such a framework, you're basically assured that packages will be compatible, and you can be sure that jax.grad works on a package that has been specifically written for JAX, for example. So in many ways, users of these frameworks don't need to understand AD at all. In Julia, we have some advantages. So in Julia, only one foo and one bar package need to exist. And this can be a big advantage because efforts on these packages can be centralized. However, compatibility with the backends is left up to the package developers and must be documented because otherwise users don't really know which backends work. And it also puts some burden on the user because it can be sort of hard to understand constraints that follow from these backends. And ideally, things should just work. So let's talk about the developer experience as well. In Python, once again, things are sort of simple. You just pick a framework and then you write code for it. Whereas in Julia, you typically first write code. So this might be some physics simulation. And at some point, you decide, oh, I would like to compute gradients over my simulation. How do I make this differentiable? And you select one of over a dozen backends. There's a very nice overview over at juliadiff.org. But one of the problems is that all of these backends come with constraints. And this is sort of the case for both ecosystems. But a big difference, which hopefully I convey on the slides, is that these constraints point in different directions. So in Python, frameworks such as JAX also have constraints. For example, they don't allow in-place mutation. But since you picked your framework, you're usually aware of these constraints before you even start to write your code. And in Julia, these constraints can sometimes come after writing your code. So in this example that I just gave you of a physics simulation, you might have to rewrite your code to make it differentiable with some of the backends. And something that makes this even harder is that some of these constraints conflict with what we think of performant Julia code, right? So usually we want to reduce allocations, we want to do in-place updates, but with some backends like Zygote, this in-place mutation is not good. So there's a lot of folklore and hidden knowledge on how to work around these things, and Guillaume will dive into this more deeply. But the question is then how to choose an AD backend and how to make it work on your code. And to understand these constraints, we will quickly tell you about the different kinds of AD systems. So there's 4 flavors of differentiation, let's say. The first one is the manual one, where you put in your blood, sweat, and tears, and manually write a gradient function that computes gradients, derivatives, whatever you want. The second one is the numeric approach, so basically finite differences, which is very flexible and can work on almost any code. Thirdly, we have symbolic differentiation, or basically computer algebra, where you give a symbolic formula for your function and get a symbolic formula for your derivative function back. And finally, we have automatic differentiation or algorithmic differentiation. So this is sort of what encompasses forward and reverse mode. And there you pass a program and get a value for your derivative, gradient, Jacobian, whatever back. Okay, so let's dive a bit deeper into this 4th point, which is automatic differentiation. And there's more or less 3 key ideas here. So programs are compositions. So this can either be a sequential chain or directed acyclic graph of elementary functions. And the multivariate chain rule then tells us that the Jacobian of such a composed function corresponds to the product of Jacobians of these individual functions within. And as you can maybe already see when you look at this equation, this can be quite memory intensive. So if we were to save all of the Jacobians of some large language model with millions of parameters and very large hidden activations, maybe we wouldn't even be able to save all of these Jacobians. So what we do instead is, instead of fully materializing them, we work with matrix vector products. So Jacobian vector products and vector Jacobian products. And if we work with the former, with Jacobian vector products, which are also sometimes called push forwards, then we end up with forward mode AD. And then here we basically accumulate these Jacobians from the right. We've added these parentheses to emphasize that we're always working with products of Jacobians and vectors. And as you can see here, this accumulation happens in the same direction as sort of the evaluation of our function, and we can therefore evaluate these Jacobian vector products in one forward pass through a function, which gives forward mode its name. And the sort of gist of all of this is that if we evaluate matrix vector products with unit basis vectors, for example, the eth unit basis vector, then this returns us the eth column of the Jacobian. So if we have an m times n Jacobian, computing the full Jacobian with forward mode requires n Jacobian vector products. And the special case of this is, of course, if you have a function with a single input, then you just need a single Jacobian vector product to compute the entire Jacobian. All right. If instead we accumulate from the other side, then we end up with reverse mode. And here we work with so-called pullbacks. And something that's left a bit implicit here is that these Jacobians are sort of linear maps at some points of linearization. And therefore, to evaluate them, you first need to compute the full forward pass of your function, save all of your activations to then compute the sort of this accumulation from the left side. What is very good about reverse mode is that we can compute a full Jacobian with just one vector Jacobian product if we have a scalar function. And this is the case for many applications in deep learning, where usually we have many inputs, so your parameters, and a single output, which is your scalar loss. And therefore, reverse mode is what is typically used there. So we have a quick summary slide here. So in forward mode, usually we have a single forward pass through your function. Typically, forward mode is based on dual numbers. And since we don't need to keep track of any intermediate computations, it has a fairly low memory cost. Whereas in reverse mode, we need both a forward and a reverse pass. We need to save all activations and these functions that compute Jacobian vector products. The data structure that saves these is often called tape or Vanguard list. And since we need to save stuff, it has a fairly high memory cost and overhead. So while these things apply with these input and output dimensionalities, if you have very small functions, sometimes forward mode is more efficient just because the overhead can be much smaller. All right, and from here on, Guillaume will take over.
Sorry to our YouTube viewers for the noise. Taking over the mic, and I'm going to tell you from this theory how you can actually use AD in practice if you're a package user and if you're a package developer. What are the most common pitfalls that you're going to run into when you try to make your own functions differentiable? So let's go. Why? The first question is, why do we have so many backends in the first place? I listed them all because I read all of their documentations. There's 12 or 13 of them. And one reason for that is, as Adrian explained, there are conflicting paradigms on how to implement differentiation in a computer. You can have numeric, symbolic, algorithmic approaches. So these require different implementations. Even within the subfield of algorithmic or automatic differentiation, there's various ways to do this. You can do this with operator overloading by basically defining new methods with custom number or array types. Or you can do it by grabbing the source code and just tweaking it until it gives you the derivative instead. But of course, there's another reason, which is historical. It was just developed by different people at different points in time. And so it is only normal for an open source ecosystem to have new packages emerging and some packages being, in a state of non-maintenance or disrepair. So it's okay. We have various choices, but as a beginner, it can feel rather daunting. So I'll try to help you figure out what to use. And here are the main criteria that you should take into account. First of all, if you try a certain automatic differentiation system, which I call backend, will it execute without throwing an error? And that's less obvious than you think. Does it return the right derivative? Because in some cases it might be wrong due to numerical errors or some more subtle forms of errors. And is it fast enough? But I can't stress it enough. You have to start with, does it execute without error? You can't optimize the shit out of it if it just doesn't run at all. So here's my decision tree. I know some people are going to yell at me, but I think for beginners this is really useful. So the first thing you want to do is, usually you're not going to use AD in a vacuum. You're going to use it as part of a larger project, for instance, involving differential equations or neural networks. And if you have a neural network library like Flux, it's usually going to tell you in its tutorials which automatic differentiation backends have been tested with it and which are reliable to work with. So first thing you want to do is follow their recommendations. If there are no recommendations, if you're in uncharted waters, then you first need to choose a mode based on the input and output dimensions. Roughly speaking, if you have many inputs and a few outputs, reverse mode is great. If you have many outputs and a few inputs, forward mode is great. And within that mode, try the most battle-tested backends. In forward mode, it's forward diff or enzyme. In reverse mode, it's zygote or enzyme. It's an oversimplification. I know. Sorry. Deal with it. And if nothing works, fall back on finite differences, because finite differences will never betray you. Now, so that was for users. Okay, now you've graduated the Julia Academy, you're a bit more confident, you're writing your first packages, and you're wondering, okay, what if I want to make the functions I write differentiable? And then you're going to run into a series of failure, and a solid 1 hour of my life every day is dedicated to debugging float64 in forward diff on discourse. So every day there's someone who comes on discourse with this typical forward diff failure. They wrote a function here, which I call bad copy. What it does is it just copies to an array full of zeros whatever's inside the input array. And when you try to compute the Jacobian of this function with forward diff, it's going to yell at you, and it's going to say, blah, 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 no method matching float64 forward diff dual. I can't stress this enough. This is what everyone will run into first when they try to use forward diff. Now, why does this happen? Adrian told us that forward mode automatic differentiation usually uses dual numbers, as you can see here. What forward diff does is it tries to propagate a specific type of number through your function, which is not just a float64. And so you have to be tolerant. You have to be open-minded. You don't have to say, okay, float64 is my life and I want nothing else. You have to let your functions breathe a little and accept more inputs. So what's going on here? When you call this method, what it actually does is it calls the underlying method zeros of float64 and the given size. In other words, this creates a vector of float64. And while it would not be a problem in your usual scenario, when you try to do automatic differentiation here, this becomes an array of dual numbers. And so what you try to do is you try to copy dual numbers into an array of float64, and of course it blows up. So what you want to do here is you want to allow numbers that have a specific type dual in your functions. And more generally, you should strive to write functions that are as generic as possible, because you never know what sort of weird magical number types people may come up with. It's not just for automatic differentiation. It's for unitful types in physics. It's for measurement uncertainties. It's for all types of things that you want to put inside your functions, and you want to get something at the end that makes sense. And if you just keep sticking to float64, you're going to miss out on the magic of the Julia ecosystem. So here, my good copy function, it accepts any type of array of any type of real numbers, and it takes into account the element type of the input when it creates the temporary storage. And with just that, I can ensure that forward diff Jacobian works as intended. So that's one example. The other one, which pops up the other half of the time on discourse, is this error. So forward diff will fail because you don't allow generic types. Zygote will fail because you mutate stuff. In my bad copy function, I had a copy to with a bang, which means it mutates its input. And here Zygote is going to tell me mutating arrays is not supported. This error occurs when you ask Zygote to differentiate operations that change elements of arrays in place. This is sufficiently explicit, but I'm highlighting it just for good measure. And so here, what you want to do is you want to either call a function which you're sure does not mutate its input, but that's not always possible. So when you have to use functions that involve mutations, for instance, for performance reasons, the right thing to do is define a custom chain rule. This is possible thanks to the awesome work of Frames on the chain rules ecosystem. And here I give you a very brief example of what it means to define a custom rule. So I define another function, badCopy2, and for this one, I'm going to tell Zygote how to differentiate it. What I'm doing here is I'm writing a reverse rule for my function when I give it input x. What is this reverse rule going to do? Remember, we're in reverse mode, so we need to, first of all, compute the output of the function, but more importantly, we need to have a way to compute vector Jacobian products. In other words, a vector Jacobian product takes a perturbation of the output and it brings it back, it pulls it back onto the input. So that's what I'm doing here. I'm defining a pullback. If I perturb my output by dy, then the corresponding perturbation of the input is going to be the vector Jacobian product, or equivalently, the transpose of the Jacobian times the vector. Okay, it just so happens that the Jacobian here is the identity. In reality, you would not code it like that, but here, just to emphasize that all we're doing is a vector Jacobian product, this is the key equation here. And so by writing this chain rule, where you compute the value of the function, but you also give it a way to work out pullbacks in the reverse pass, then when you call zygote.jacobian on your new function, you see that your rule is called when it tries to differentiate through the function, and the inner pullback here is called as well twice, because as we saw, we need 2 pullbacks when we have 2 output dimensions. So all this to say, when you have a function which is not supported by zygote, most of the time you will want to either change your function, or if it's not possible, write a custom rule knowing what you know about your mathematical model. And it looks hard, but Chain Rules Core is probably one of the Julia packages with the best documentation out there. So this taught me all I know about automatic differentiation. Really read it, it's worth a try. And now you also have Enzyme, which is the kind of new kid in town. And it's like way more powerful than the other kids. But it's also, it has a bit of an attitude, right? And so you need to know how to handle it. And in particular, it has this whole mechanism around activities specification. Basically saying this argument needs to be differentiated, this argument doesn't need to be differentiated, and you need to know how to work your way around it. So you'll often see errors that are linked to the way that you specify the activity of your inputs. And for that, there's a brand new FAQ in the Enzyme documentation that goes into more details on how you can solve these types of bugs. But so these were the 3 main types of problems that you'll encounter when you work your way through automatic differentiation. And it's important to emphasize this is structural. No automatic differentiation system is going to be perfect, handling 100% of the Julia code base with no errors. That's not going to happen. So anything you choose, it's going to have advantages and drawbacks, and you need to work with them. Now, this all started with a very late Slack conversation between me and Adrian, and one of us said, well, we need to give users a way to call automatic differentiation without diving into the documentation of every single package. And so that's how differentiation interface, or DI for the people in the know, was born. The goal is to offer common syntax for all of these backends so that you may switch them by just toggling an object instead of going through each documentation and figuring out, wait, is it called Jacobian or is it called pullback? How many arguments does it take? In which order? How do I parse the result? Do I need to specify activities? How do I specify the cache? How do I record the tape? Etc., etc. I know all this because I coded all this for you, so you don't have to. In advanced use, you may want to call the backend's API directly because of some subtle performance issues, but for 99% of beginners, I would say this is soon to become a good way to start auto-diffing through stuff. AD users can so compare correctness and performance between backends, and developers get access to a wider user base. How does it work? Well, first of all, it supports every autodiff package out there. All of them, and the ones that are being developed, like ADOLC or GTPSA, are also adding support. So it's as comprehensive as it can be. And it's fairly simple. So the way it works is you using differentiation interface, and you import any backends that you may want to use, and you define a function and an input. And here, for instance, we're going to compute gradients, which is one of DI's operators. And the only thing that changes between the different backends is this object here, which is taken from AD types. And if I want to use forward diff under the hood, I say compute the gradient of this function with forward diff. If I want to use enzyme instead, I use the exact same syntax. I just change this object to auto enzyme. If I want to use zygote, no big deal, same syntax. Same syntax, different libraries. And this allows you to compare their performance and correctness. Once you are done with that, you can increase performance because DI also has a preparation mechanism for things like tape recording or cache, etc. But again, that's something that the user doesn't have to dig into to figure out. I dug into it, and it only has to be done once instead of doing it for every single package out there. Now, it has several features that I want to briefly mention. It supports right now only scalar or array inputs and outputs with either 1 argument or 2 arguments, but we're going to probably work on that Saturday. It has the standard operators that you would need in your day-to-day life, push forward, pullback, and then derivatives, gradients, Jacobians, even higher order like Hessians. For the weird people in the back who want higher order differentiation, third order, fourth order, don't look at me. I won't do it. There's out of place and in place versions, and you can have a few niceties like combining different backends or translating between backends. If something is differentiable with one but not the other, you can sort of translate under the hood with this structure. It also has a sister package called Differentiation Interface Test that allows you to compare backends systematically and even with weird scenarios like static arrays, GPU arrays, and it does automatic benchmarking. It has a brand new sparse AD ecosystem, which is kind of Adrian's baby, with sparse connectivity tracer for sparsity pattern detection, few utilities for matrix coloring. The gist of it is that you compute Jacobians by computing one column at a time. But if there's lots of zeros, you can actually compute columns, several columns at a time, and then decompress the result. And that gives you beyond insane speedups if it's done properly. Now, to conclude, all of this is brand new. Like, all of this is less than 6 months old. I'm not pretending it's going to be the best performance that you can get on every single problem. What I am pretending is that we are extremely responsive. So if you want to help us get this to the level where it needs to be, try it out in your code, report bugs, open issues, and yeah, help us make this even better. Now, of course, there's plenty of things I left out. If you want to AD through a simple function, that's great. But if you want to AD through an integral, an optimization solver, a stochastic expectation, there's more stuff out there in the ecosystem, especially in the SciML world and also in my research on discrete combinatorial solvers. You can find more details in this book. The take-home message is the following. Computing derivatives is easy. It's 2024. You don't compute derivatives by hand. That's over. But as soon as you use automatic differentiations, it comes with its own limitations. So learn to recognize them, learn to overcome them, and I think you're going to have fun. We have time for questions, but not from Chris.
Okay, thank you guys. Awesome talk. Yeah, we have time for some questions. Anyone want to get us started? Raise your hand if you have a question. I'll come to you with the mic.
Thanks a lot. So I was wondering, so what's the best way, let's say I have two arrays and I want to do reverse mode automatic differentiation, and sometimes I only want to differentiate with respect to x and y, or sometimes maybe both. So is there an easy way to specify, enable, disable some of the gradients?
So in differentiation interface, not at the moment. In Enzyme, yes. In Enzyme, it's pretty much the only backend that supports this. So that also explains why DI cannot do this yet, but perhaps next week it can. So the development is really that fast. So yeah, this is on the top of my bucket list.
So maybe a quick follow-up. So I would wrap everything into a component vector if I want to use like bigger, like x and y, right? Because you only accept single arguments.
Right now, that's what you need to do. Again, I'm going to work on this Saturday during the hackathon. So the next big thing I want to do is figure out a way to pass multiple arguments and specify which of them are differentiable and which of them are constant.
While I'm walking, all you guys in the back, there's a whole bunch of seats here in the front. So in the break, go ahead and move up.
Thank you. Thanks so much for the talk. It was great. I wanted to ask, would you be able to say anything to the broader ecosystem in which order differentiation is situated? Like, for example, I found out about AD through Flux, and that meant I only knew about Zygote. I learned about Enzyme today. Is there plans for DI to kind of be integrated with Flux or Lux or any other kind of higher libraries?
Again, this is kind of a very new project, and we started with the simplest setting, which is like functions of one argument with arrays, essentially. And it may look simple, but it already covers the use cases of some big packages like optimization.jl or ordinary differential equations. So that's kind of our first target. We've been working with Chris quite closely to get the SciML ecosystem to use this. The next big target is, on the one hand, deep learning. And for deep learning, it's more complicated because the layer structures inside Lux and Flux, they're not just arrays. So that's essentially a rather hard thing to handle, because you can't pretend with 100% certainty I can handle every struct out there. The imagination of Julia developers is endless, and they'll always find something to break your stuff. So the question is not whether we can pretend to support arbitrary structures. The question is whether we can test reliably enough what we support to be useful in Lux and Flux. And it's feasible. We have the infrastructure to do it. It's just a matter of Lux and Flux defining what kind of test suite would give them confidence in the code that we wrote. Yeah, maybe Sunday, right?
Yeah. Thanks a lot for your talk and for your effort. I think a bit about all the limitations that you said across all these packages. So you have to pick and choose, but I actually find myself needing to use multiple of these automatic differentiations. So I want to, maybe just to give you an idea, I want to train a neural SDE and I want to use Zygote, for example, but it doesn't work for my case because I need to do, or it doesn't work for specific cases like SDE. So I find myself wanting to use something else. And then I have to pick and choose between a couple of these libraries. Is this good behavior, or I shouldn't be doing this?
So if you go back to my decision tree, I'm not an expert on differential equations and the like. So this is really SciML realm. Yeah. The first answer would be use whatever SciML tells you to use. If you use a neural PDE or whatever and you're using it from a package, then do whatever that package tells you in its tutorials, because that's the way that it's tested. Now, if it doesn't work, differentiation interface is a very good way to experiment, because switching a backend is as easy as just toggling the object where you choose it. And yeah, basically, if you need to do something custom that is not covered by an existing package, open issues wherever the AD backend that you chose doesn't work, to see if it's fundamental or if it can be overcome.
Yeah, maybe one sentence on this also. So maybe what you're looking for is also this differentiate with function, which allows you to automatically generate custom reverse, forward, and reverse rules by calling other backends. So we're sort of pretending to implement forward or reverse rule, but we're actually calling another backend in the background. So that's something that maybe you would have written by hand, but that you can now use through differentiation interface.
I'm sorry, I think this is all the time we have. If everyone can give Guillaume and Adrian a hand, sorry. And we can get that switched. Okay, so, yeah. Please, or everyone that's in the back, please don't be afraid. You can come up to the front here. There's a lot of seats. Everyone's very nice. Well, oh. Mostly it's the I'm moderating, but it's the crowd around. It's the 5 minutes to switch over the speakers, get questions. And you need in the mic. Okay. I wasn't supposed to be the moderator, so I have no idea who anyone I'm introducing is.
Thank you. He can help. But let him be the moderator. So Julia.
Yeah. Well, he's speaking right now.
Wait, do you guys need a moderator?
No. No.
We could do it one more. Do you want to volunteer?
Sure, what do you need me to do?
We need you to introduce the speakers nicely so he can do the microphone duty up and down, right?
Sure.
Do you know who's talking?
I know Julian.
Good. If you know Julian, tell a fun fact about Julian.
He's got a great beard.
Okay, beard is good. We can run with that.
Okay, great.
Thank you very much.
Yeah, of course. You just need the intro?
Yeah, just do an intro.
Try
Okay.
to do better than me on names.
Whose laptop?
Okay.
Real low.
What's your name?
Dheera.
Dheera?
Dheera, yeah.
Dheera?
Yeah.
Okay.
Standard, you guys, 5 minutes for the yellow card, 1 minute to go with the red card, and then it should be 5 minutes at the end for questions. Cool. Keep the timer up.
All right, cool. Thanks, everybody, for coming to this talk. This is Dheera. Close enough, right? I'm sorry. And this is Julian, and they're going to talk today about training Llama 2 in Dagger.jl, and you guys use Flux, is that right? Yeah, so this should be a very cool talk, because this is not a thing that we normally do in Julia. So I'm excited. Yeah, good luck.
Thank you.
Thank you.
All right. Hey, everyone. Microphone. There we go. So I'm Julian Samru. We've been working on training Llama 2 in Julia with Dagger.jl and Flux.jl.
So that's our little llama that hopefully by the end of this talk we would have trained to do something interesting, right? So the first question is why? Why would you want to do that? Everyone uses PyTorch anyway, right? There's a very, very big ecosystem of models that are trained to perform many, many specialized tasks already existing in the Python ecosystem, along with a lot of tooling to actually help deploy them as well as fine-tune them on various other tasks as well. So why do we want to go ahead with Julia in this case? Well, the tooling in Python is not perfect. A lot of these tools that we do see don't actually interact with each other that well. A very common example could be something like trying to use Number with Torch. Up until recently, doing that was also quite hard, and the setup involved was extremely non-trivial. Especially if you want to do anything at scale, that means that you now have extra overhead, so to speak, to actually set up the various libraries and the binary dependencies that come with setting up a large training routine. So while PyTorch is great, it has many available operators, it is completely GPU capable, well tested. The GPU support, unfortunately, is super inconsistent. While it is possible that you have something as cool as NVIDIA working, but support for AMD, for example, which is, again, a big vendor, is not really there yet. It's very difficult to write generic code, and even the generic code that we do have often comes with compromises of its own. As is very commonly known, Python front end is backed by a lot of C and C++ underneath it.
And also, just pointing out, CUDA and AMD, or NVIDIA and AMD, are not the only two GPU vendors. We also have Apple GPUs. We also have Intel GPUs. Support for those is meh.
So Python does come with its own challenges, right? As we spoke about earlier, Python packaging is kind of a mess. Actually getting the package manager to cooperate is itself a bit of a task. Python itself might be slow. It needs the tool language problem to actually be performant by for modern machine learning tasks at this point. It is also extremely hard to write new operators, as we spoke about. The amount of boilerplate as well as setup code required to actually make Python do anything fast is pretty hard. Multiprocessing and multithreading story in Python is slowly evolving, but at this point, it is something that is much, much easier to do in Julia as it stands.
So maybe we should just use Julia. So what is the state of Julia's Llama 2 support? So we do have Llama 2 packages in Julia. There's llama2.jl, there's transformers.jl, there's some other ones I'm not remembering right now. They have support for inference. There's support for training on CPUs. Maybe transformers.jl has support for GPU training. Not really out there, not really been well tested. Transformers.jl is great. It has a lot of flexibility. It's got a lot of, you can build your own LLM models with it. It's quite verbose. It's not something that you're going to do in maybe 20 lines. And no quantization support. What specifically you can load, at least with llama2.jl, you can load quantized GGUF weights, but you can't actually work with them in memory or on the GPU. You have to dequantize to float 32 first, so that is quite unfortunate. So what do we do?
So let's talk a little bit about the trends in how machine learning workflows in the modern age have actually grown. So as we can see, this is a graph that shows the size of the data sets that have been trained over time, starting from about the 80s, late 80s till modern day. We can see a large spike at the top right, and this actually happened very close to when quantization support was something that was featured more heavily in training routines. As we can see, very clearly it shows the hunger for more data, for bigger models, and with that comes the necessity to actually manage this much data, manage this many parameters in our models. So how do we actually tame this beast? Well, quantization is therefore a very, very big need at this point for us to actually scale our training processes beyond a single node GPU. This leads us to the next point. How do we actually go about parallelizing our training processes? we have many options, but knowing that we have an ever-increasing number of parameters in our models, an ever-increasing amount of data that we need to train on, and super specialized tasks that go with them, how do we actually decide what is the most scalable manner for us to train modern machine learning workflows, especially in the presence of non-standard training routines?
To start with, right, before we look at the various ways that you can actually parallelize things, parallelize large language models or other machine learning AI models, just to point out, we said before that this is using the work that we're doing is using flux.jl and dagger.jl. Flux.jl has great autodiff support via zygote.jl, has this fmap helper that we'll see a little bit later for applying functions and operations to all of the gradients in a model. Quite convenient if you've ended up using it. It comes with quite a lot of general purpose machine learning utilities, various losses, optimizers, like the kitchen sink, everything is in there that you need. And of course, it's GPU enabled. This is providing basically our machine learning AI scaffolding for what we're going to be doing. And then Dagger.jl is basically providing task parallelism APIs that we're going to build on. Supports threads and workers, so multi-threading, multi-processing, has a cross-vendor GPU API. As I was saying before, there's not just 2 GPU vendors, there's at least 4. Support for all 4 of them is available and tested, and allows us to flexibly deploy training for basically most of the compute architectures you're going to see out there. So what are our possible approaches for parallelizing here? So there's basically 3, there's more than this, but these are the 3 most common. There's model parallelism where, okay, maybe you have a branch in your model and you have 2 kind of independent paths that you take through the model when you're doing inference or doing training. So, okay, you can execute those in parallel. You can run one on one task, one on another. Maybe that's one thread, another thread, one GPU, another GPU. Then there's operator parallelism. So this is exemplified in, say, like matrix multiply. You use BLOS. BLOS is multi-threaded. BLOS can do, use GPUs, stuff like that. Various other operators support this. And then there's this third one called distributed data parallel, or DDP. So this one is what we're going to talk about today. Real quick, the first 2, limited parallelism. There's not a lot of cases you can apply model parallelism, and operator parallelism doesn't necessarily always get you that far. Both can bottleneck in quite a lot of cases. DDP, which we're going to talk about, is quite scalable.
Let's talk about what basically DDP allows us to do, right? The idea behind it is simply that we use some kind of already used collectives over large batch sizes across multiple devices, which themselves get synchronized together and then shared back to actually optimize our models. So typically you would end up with having multiple copies of the model on various devices. Each then gets their own data set or sort of a shard of a mini batch, which then together coalesces back to form a singular gradient and then passes that back and uses that to update all the copies of the model. So this is a very, very common scheme and has been implemented many times in different forms. Its generalization is this concept of single program multiple data, or SPMD. Something like this is very predominantly used in MPI, and for that matter, even the GPU stack is built on very, very similar ideologies. So what are the benefits? It allows us to scale basically as many times as we have devices. So as long as we can keep adding devices and nodes, we can keep increasing the amount of compute we have and increase the amount of training we're able to do at any given point in time. Beyond that, it is quite simple to set up. The basic building blocks of SPMD, as I alluded to earlier, is quite easy to actually express, which means that we get a lot more flexibility in how we get to deploy it, especially in terms of, in the presence of training routines that are not standard, and something like an LLM definitely doesn't count as a standard neural network, considering how much data we have to deal with. Managing all that memory becomes a big bottleneck.
And yeah, more and more models are getting ever more complex. So this is an approach that is scalable also into the future. Just real quick, what we have up here, sorry if the font is a little bit small. We have, this is basically just how we've implemented SPMD, or the core component to DDP, where basically you just have this SPMD region. You have a rank. If you're familiar with MPI or CUDA, in MPI, we call it a rank. And in CUDA, it's a lane or a thread. Basically, the idea is you get an integer index, which is unique to each thread and tells you what piece of data you're working on. So we have an API for that. And the idea we're showing here is basically you can just write your loop, walk through iteration by iteration, updating your variables locally. This is happening in parallel on multiple ranks. Those can be multiple threads, multiple GPUs, whatever. And then whenever you need to, you call a collective operation. And a collective operation is just basically saying all of the threads or ranks or whatever you want to call them all cooperate to update their values together because they depend on each other's values. In this case, we created an array X, and then we just did what's called an all reduce, just summing all of the values together and then just writing them back into X. Super simple operator, one line. So how does SPMD actually work? So the way we've implemented it on top of Dagger.jl just creates a set of Dagger tasks. Each task has its own rank, as I said before. And then during a collective reduction, as we saw on the last slide, it uses a highly parallel GPU-aware Dagger-powered ring reduce. Ring reduce is one of those very efficient ways to do an all-reduce operation. It is typically pretty hard to optimize, especially on like a supercomputer, which is where most of the research usually is. But it's difficult even across threads and GPUs. These are just kind of the system that this is built on performs very well in a highly parallel setting.
So what's missing at this point? We spoke about already having Llama packages. So we have Llama 2, we have language models.jl. We already have a Dagger-based API which allows us to implement an SPMD routine. Well, just add a little bit of data parallelism and there you go. I mean, what's really missing? Turns out not much and also quite a lot. Let's start digging into these things one by one, right? Llama2.jl, while a very capable package and actually is very highly optimized as well in terms of CPU compute, does not actually have support for a lot of training routines, especially on the GPU, right? Because as we'll see later, managing this much data actually requires us to have a lot of parallel compute that's available to us. But if you were to go through this little piece of code right here, right, I want to also want to highlight how simple this is and how familiar it might be to someone who's already written or seen how a flux training routine works. On the top, you basically start with some setup. So you load some data, you take your model, and we just have helper routines for that. You have your optimizer and you set up that optimizer. This is pretty standard. Well, the next little bit is also fairly standard for those of you who've already written Flux routines, which is you basically start a loop, right? And in that loop, you typically have a loss, and you calculate gradients of your parameters over that loss, and then you optimize. Well, there's just one little piece of code that we've added in the mix, right? And this is where we actually do our parallel reductions. So we spoke about why the fmap was helpful. Well, it just so happens that because we have these basically nested tree objects inside our gradients, we want to basically collect all of them, but not actually pause all the training, the loop that is actually going on, right? So we want to synchronize at one point in time, actually collect all of it, do a reduction, and then spread that back around. So as you can see here, our all reduce is basically just going to sum over all of our gradients and then do an average in this case. Very, very simple. And then our existing packages can just then update the model state, because even though this loop is actually happening in parallel, it appears as if everything literally was happening in a local for loop that we are all familiar with.
Oh, and quick comment. This is not specific to Llama 2. This loop is very easy to apply to basically any model. Yep.
Yeah, I should also talk about this routine is something that is not limited just for the packages that we've written or the models that we've written. They can be applied to downstream tasks just as easily as well. Of course, things are easier said than done, but fundamentally, the building blocks are all there and the building blocks are generic, which means that even though we're just composing existing packages, we still get the ability to actually express any kind of model that you would typically as a Flux model, and then simply make it parallel by adding very, very simple primitives in the middle as well. So let's talk a little bit about the benchmarks. As I said earlier, Llama 2 currently only supports CPUs. Transformers doesn't unfortunately have support for the GGUF weights that we're going to be testing with, which makes it a little bit, it wouldn't be a fair comparison. And so it's really hard for us to compare across packages. And this was expected, but still quite a shock for me personally, because you would expect for an ecosystem which already we know has the support for these models, it is still quite in its early stages, and that is highlighted by the fact that we don't actually have a unified routine to manage all of these things and compare across them in a nice, consistent way. So this is just a simple run that we had done for managing our training runs. You can see the model config at the top there. We used the weights and the pre-trained models out of Hugging Face, and this is effectively the config that Llama 2 would actually give you. Both those models were trained exactly with the same config on the same data set. As alluded to earlier, Llama 2 does not unfortunately have support for GPU training, so just as a reference, this is with the Flux model, but it's within spitting distance of the Llama 2 implementation itself. Important to note here, the first number that you see here is actually just the forwards pass for a large enough batch size, and the second number is for the reverse pass, the backwards pass. Whereas on an NVIDIA V100, because again we as long as we use array operations throughout, and LLMs use mostly just array operations throughout, we can benefit from existing kernels that exist for all of the various operations that we have to do, your multi-headed attention, your rope, and so on, your positional encoding. So luckily that means that we have a mature enough GPU ecosystem at this point that time per mini batch is pretty manageable at this point. We can see that we can genuinely, even on a single GPU, get a decent amount of performance. And because as we mentioned, this model is pretty scalable. As you add GPUs, you can actually increase the amount of data that you're passing through your model, and naturally get scaling from there as well.
And we also expect that we can optimize these numbers a bit as well with a little bit more work. So this, at least for the GPU side, this can get better. Notably, there are some missing features. So we did discuss, well, I'll start with the second one first. We did discuss quantization support as being extremely important. That is another area where performance will improve over time. So this is something that we definitely would love help with. It's a good bit of work to implement the full support for all of the quantization operators that llama.cpp, kind of the like gold standard for llama, supports.
So quantization support goes beyond just having a number type. Our ecosystem is basically written to be extremely composable, which means that we have a number of packages that come into play for the simplest of operations, and something like a large language model is definitely not, right? So we're talking that same support going from the highest level of abstraction from the model itself down to our AD, our kernels that we write, to actually having those operations implemented in the GPU backends, be that CUDA, AMD, and so on, as well as then within base Julia itself. Basically saying anytime we actually lose the quantization effects, that is to say anytime we have to make a copy or convert to a large format, large floating point format, we end up with the same kind of performance that you would otherwise expect. Now that is not a small or an easy task, right? It requires the entire community to come together to actually, basically chip away at the various pieces.
And then additionally, one thing we had not had the chance to get to was LoRa fine-tuning support. This is additionally something we would love help with. I don't believe Llama 2.jl supports LoRa fine-tuning.
Not Llama.jl, yeah.
Yeah. Real quickly, the challenges that we went through when working on this: GPUs have less memory than CPUs, which exacerbates the problem that the GC doesn't always like what I do in Dagger and what Julia's distributed.jl does. I promise they're all regular, normal things. The GC doesn't like it. The SPMD implementation is pretty new. There is the potential for some deadlocks, and it's not always the most user-friendly, so we're working on improving that so it's easier for users to apply. Distributed.jl is buggy. If you saw my Dagger workshop on Tuesday, you're quite aware of this. And then Zygote can't auto-differentiate in-place operations, so our memory footprint and the GC issues that causes, it becomes a problem. This is something that we want to take a look at pretty intensely over the next few months. And then numerical AD issues are always kind of hard to debug.
One small point that I wanted to make was luckily this list of challenges is something that the larger community is aware of and is pretty commonly known, right? Like these are challenges that we all have faced over and over again in different forms in different places. So I do expect, over time, all of these things to improve quite substantially. So to conclude, basically what we ended up doing was we have now a Flux-backed Llama 2 implementation, which means that it is doing things a little bit out of place, but more or less is able to compose well with downstream packages that also allow usage of Flux models or just functions in general. We implemented a pure DDP training loop, i.e. there was really no dependencies to speak of and or setup for that matter. It was pretty easy to go from running on my laptop on CPU threads to putting it on a server which had a GPU, and then beyond to a node which had multiples. Luckily, this also means that we can therefore support basically any model that. Whoops, this screen just went. Okay, never mind. We can support basically any model, right? Because it is built on top of these composable building blocks. And basically any GPU backend that Julia has support for. Okay, so and finally, Llama can train with multiple CPUs and multiple GPUs. So we've spoken about that.
And just real quick, we would love help with all of these things. So if you're able to help out or really interested in learning how all of this works, we would love you to reach out and just give us a hand with this so we can make this really work super well and beat Python.
Okay, yeah, that's our talk. Thank you.
Okay. As always, yeah, if you want to help, if you have more in-depth questions, you can always find them after the talk and corner them and ask them all the questions you want. For now, we have time for 1 or 2 questions.
Hi, thanks for the talk. So building on what you said right at the end, do you have any idea how your training compares in terms of benchmarks with like PyTorch or JAX or some of those frameworks?
So again, the kind of comparisons that we would want to make were not very trivial. The same kind of issues that came up when we tried to compare across the Julia ecosystem, well, get exacerbated once we include Python in the mix, right? Because not only now do they have support for something like a quantization or a LoRa or whatever, the problem completely changes all of a sudden. So no, in our study we did not actually compare strictly against Python benchmarks, but that is purely because it would not be a fair comparison anyway.
Okay, thank you.
Other questions?
Thanks for your talk. Quick question. So assuming I have some cluster somewhere that has AMD, NVIDIA, Intel, and maybe some Mac connected to the system, could this already run the compute across these 4 different hardwares, given the abstraction?
The answer is, I will say technically yes. All of the infrastructure is set up to support that. I would say whether you're running multiple different vendors on a single system, or if you're just wanting to try out, a training run on one kind of GPU, a training run on a different kind of GPU, but keeping that all homogeneous, that should definitely be pretty easy to support. Works already. Everything that this builds on is supports all the 4 main vendors right now. So give it a try. If you run into trouble, just let us know and we can fix up anything we find.
That's great. Thanks.
I think that we can do one more question.
Hi. Well, thank you very much for the talk. It was very interesting. I don't know, maybe this question is more for the developers of Metal.jl, but since you were talking about the flexibility that Julia has compared to Python or to the other frameworks, I know that the ARM processors from Mac have a GPU, but also a machine learning processor specific that with all of this coming from AI everywhere, I think that the machine learning processors in the Macs and also in other computers will get larger, and it will be very convenient, and it will be a large advantage over Python, for example, if we could use that power. And I don't know if that will be possible at any time or not, or if it is completely different from a GPU.
Yeah, we are aiming to be as generic as possible with these codes so that we are able to hit dispatches within, say, Metal.jl that allow us to use various tensor hardware, stuff like that, use vendor BLOS or whatever, whatever the most efficient and available thing is. So yes, definitely that is something that we can support with this. If it's not currently supported, I think it's just something, file an issue on Metal, and then the GPU developers can take a look at it and get that implemented. But all of this would be able to use that.
Okay, that's all the time we have now. There's going to be a short break, but do come back. There's going to be a series of 10-minute talks with more on AI after that, and then even more talks after that. Okay, I think maybe we get started. Probably get some more people coming in from the break, but hopefully they'll be quiet. So, introductions here for Polito and end-to-end AI. And hand it over to you.
Yeah, thank you very much. So I'm Paulito Palmes from IBM Research, specifically from Dublin. I like the ambience of this because usually we present in the pub, so I like the pub setting, which is really appropriate for people from Dublin. So here's the outline of my presentation. So first is the motivation behind the end-to-end AI. What are the main components of end-to-end AI, the Julia AI ML's use case, and then the future. So what's the motivation behind it? So currently, if you're familiar with the infrastructure as a code thing and the ML ops, they are quite separate, so that when you try to solve a problem, the assumption is that the infrastructure is already there. But we know that for every deployment that you need an appropriate infrastructure to do that. Without the proper association between them, it's very difficult to infer in the future if you have a new deployment or a new AI solution, what kind of infrastructure you need. So if you place them together, it will be easy later in the future to say that I have this deployment, how much CPU I need, how big is my memory, how big is the infrastructure that I need. And in the future, we are also targeting intent-driven kind of end-to-end AI, where you can just talk to the ChatGPT or LLM to say that this is my intent, this is my experiment, can you give me a YAML configuration to do the infrastructure as well as the ML ops? And that's the dream. So here's the main component. So basically, you need to have a YAML workflow, and that YAML describes your infrastructure as well as the ML pipeline, as well as the lifecycle management. Lifecycle management means that you need to have a certain kind of monitoring when you deploy your application, so that when the model is drifting, you need to retrain it. If your infrastructure is drifting, you either scale up or scale down. So you have like you're training an ML, but there's another ML that tries to monitor it. Okay, so there are so many components, and I'm just going to talk about the components above. So data orchestration, pipeline orchestration, and then infrastructure orchestration. The moment you finish this orchestration, you need to deploy them. Take note that when you do this kind of deployment, infrastructure is ephemeral. The moment you don't need it, you delete it. So automation is very important. Training is ephemeral also. Once you finish the training, together with that infrastructure, you delete it because you deploy it in somewhere where the deployment usually don't need a lot of resources because you're not doing a lot of training anymore. So there's a separate kind of thing. So a lot of these things that I'm doing here is automation. If you want to deploy later your Kubernetes cluster at home, or if you have some extra machine, you can use the script, and within 10 minutes you have Kubernetes infrastructure to play with. So by the way, this is partially funded by the EU project for 3 years, and we are doing experiment to support experimentation in 6G, which will happen all around 10 years from now. And we are talking about terahertz of speed. Okay, so before doing the end-to-end AI, let me refresh you of the package that I created a while ago about pipeline optimization using AutoML. So basically, let's start with loading some of the components of end-to-end AI, like you have certain kind of scaling kind of components, feature extraction components, and then learning components. And the beauty of this is that you can have a one-liner to do this pipeline thing, and you can evaluate that particular pipeline. So here's an example. So I have a data set. The purpose, the idea is that this is my my target. I want to predict whether the football game is away or at home, and these are the features. And I choose this data set because there are some columns here that are non-numeric, so you need to do certain kind of pipeline transformation. So first transformation is that I will select the categorical features from that features and heartbeat encoded, and this is the result. So that's one liner. And there are only 2 APIs, fit, transform, and then cross-validation. So another example is that I have 2 blocks here. The first block is that I want to get the numerical features, transform it into PCA, and the same numerical features, transform it to ICA, and concatenate the two blocks. So that's another feature. Okay, so now this is another example. So this is now typically become more complex because you have now scaling plus extraction, feature extraction, then another scaling plus feature extraction. Take note that the more you add different kinds of components, the performance of your pipeline may improve or not. So lastly, if you placed at the last part of your pipeline your random forest, you can change the fit transform API into cross validation, which means to say that for this given pipeline, what is the performance of my my pipeline given a data set? So let's try to run this if this is quick. Okay, so this is 66% for random forest. If you do the SVM, linear SVM, it's 72% or 73%. So if you ask me which learner is the best, you will not know until you run the pipelines and corresponding to the data. Okay, so you can also do a lot of this parallel processing in Julia. So for example, I want to search for the best learner for a given pipeline. I can do that. And then this is the best pipeline, right? So that's basically the AI solution that I have, and I want this to be integrated in my end-to-end AI framework. So this is the end-to-end AI application. So what you're gonna do, you list down all your machines, the IP address, you choose one of them as the controller, the rest are workers. And then if you follow the IAC script, you will have your cluster like this in less than 5 minutes, maybe, or 10 minutes. Together with that is the observability, because when you try to run your pipeline, you need to observe the status of your network, the status of your cluster, so that when something goes wrong later, you can do anomaly detection. And I use this data set to develop anomaly detection later also. So this is like doing this platform for your development at the same time as a research. And we have published something related to anomaly detection. And then you have this kind of, together with this is a template where instead of creating your program, we already created a template for you. And all you have to do is just change the data and the kind of problem that you want to solve. And this template basically outlines the step to do the prediction or the regression. So here's an example. You can just imagine that each of these steps is a Dockerized solution. It can be written in Julia, in R, in Python, and so on. So here is an example here. This is written in R. This is written in Rust. This is written in Rust. This is auto scikit-learn. So the beauty of this framework is that you can Dockerize your solution, and it's agnostic about programming language. Because this is Julia, I'm using my AutoML pipeline to run this AutoML in that framework. So here's an example where you just submit, for example, the data set. You can change the worker. The complexity means that you want to have a longer kind of blocks. And then you can also even decide to run both sides, where I need to check whether the low complexity is good enough, because low complexity means that the processing will only examine 24 pipelines instead of 576 pipelines. And it can be much more depending on your data set. Okay, so here's more example. And this is an example of the templates that I have. And this is the one that you can change. You can override the templates, and eventually it will be called here. And this is your Dockerized solution, and this becomes your arguments. And this is the vision of the future. We want to connect them together so that you can move your resources to the most appropriate locations of your nodes that have much better GPUs, for example. And with that, I end my presentation. Thank you very much.
Okay, we have time for one question. Does anyone?
Yeah, great talk. Thank you for all that. I was wondering, you mentioned it would be AI as a service. Would that mean someone would just upload data, then download a model, and that would be the basic flow of it?
Yeah. So everything, there's an object store basically that you upload your data in that object store, and then you point you can specify in your YAML workflow the location of the data, and everything will run. Yeah.
Thank you.
Good question. Thank you very much.
Okay, for our second lightning talk, we have Adrian with Explainable AI. This should be quite an interesting talk for anyone that's curious about what's going on inside the black box of these AI models that everyone gets so excited about. Nice. Okay, hello. Yeah, if you want to follow along, you can start out by scanning the QR code. My name is Adrian Hill. I'm a PhD student at TU Berlin, more specifically in the machine learning group under Bifold. And today I will tell you what's new with explainable AI in Julia. So at JuliaCon 2022, I presented my package, explainableai.jl, and today I'm happy to announce that this package has grown to an entire ecosystem and organization, and this talk will more or less be an invitation for you to join in this ecosystem. So this morning we already had a talk on trustworthy AI by Patrick. What we are looking at specifically, Yes, great. So what we're looking at specifically are post hoc local input space explanations of black box models. So what does this mean in simpler terms? What we want to look at is which parts of the inputs into a model are responsible for the model's outputs. And more specifically, we're going to look at classifiers here. So let's start out with a motivating example. We have this image of a castle in front of a busy street. And we start out by loading pre-trained machine learning models. So in this case, using Flux and Metalhead. And once we've loaded this model, we can evaluate it on the input and get a prediction. And in this case, the model correctly returns class 484, which corresponds to the castle in ImageNet. So we got the correct answer. That's a great first step. But if we use such classifiers for more crucial decision-making processes, we might want to know why this class was predicted. So this is where several of these explainable AI methods come in, some of which I've presented last time. So general gradient-based methods are part of explainableai.jl, which is a package that can be used on any differentiable classifier. So it's not only Flux, but also MLJ compatible. And we also have a new package, relevance propagation, .jl, which implements methods which need definitions of usual machine learning model layers. So here we've opted for flux.jl. And in these packages, we have several new methods. For example, support for ResNets and newer transformer architectures in layer-wise relevance propagation. All right, so what does it look like to use these packages? Well, if you've already loaded your pre-trained model, it's quite simple. You import one method package, so in this case, explainable AI, and one visualization package. So here I've opted for vision heat maps, since I'm dealing with a vision model. And then I create an analyzer. In this case, I've used the gradient analyzer, which basically computes input sensitivity. So just the gradient of my output class with respect to my input image. So not the parameters, but the image. And the API is very simple. I just call analyze on an input and an analyzer, and I get an explanation. And if I then call vision heatmap's heatmap function on this explanation, I get a heat map. And I don't know if it's very well visible for you, but the magnitude of the gradients is slightly higher in the domain where the castle was located at. And yeah, this is maybe not the most convincing explanation. It's due to a phenomenon called the shattered gradient problem, but that's why people have come up with other methods as well. So I could also just swap out my analyzer. So I've just changed the third line of code. I've swapped the gradient analyzer for gradcam, and then
this method will give me a different type of heat map. All right. What I can then do is use a completely different package for completely different methods. So here I swap out explainable AI.jl for relevance propagation, and I can evaluate this method called layer-wise relevance propagation. And here I get different relevance scores. So pixels that have contributed positively towards an explanation are highlighted in red, whereas things that have contributed negatively are highlighted in blue. So that's maybe this street in the lower right corner, and things that didn't have so much influence are left white. Okay, so how does all of this work? Well, basically, methods and visualization packages both built on a common interface that is defined in XAI base, so explainable AI base. And this defines an interface, an explanation type, which is just a very generic wrapper type to dispatch on. It gives you shared utilities to select outputs of a classifier, and also intermediate features if that's something that the method requires. And yeah, if we then use Sybase and Flux, we can write a package like relevance propagation. And you're also kindly invited to build on this common interface and add your own custom XAI packages. So we've seen some of these methods. Let's maybe dig a bit deeper into the visualizations and the interface. Vision heat maps is basically a package that breaks out the previous heat mapping functionality from explainable AI. As before, you have some utilities. You can have default heat mapping settings based on your method that you use to generate the explanation. You can override all of these presets by specifying custom color schemes or methods to reduce color channels to a single scalar number that can then be mapped to a color scheme. I've also previously shown a new function called heat map overlay in the context of GradCam, which basically overlays your heat map over the original image, which can be nice to sort of understand the decision as a human. And then this was highly requested at the last sort of JuliaCon 2022 is textheatmaps.jl. So with new language models on the rise, I think it's important to be able to visualize classifications on text as well. And basically, you can just assign numbers to each of the words, or tokens. You could break this up however you want, and then we can just visualize this for you. This works in HTML, so in Pluto notebooks. Here in Quarto, it also prints the words in color for you in the REPL, so that can be very nice if you prefer an interactive workflow. All right. Yeah. Finally, the interface. It's quite simple. So the only thing you need to do is that your method has to subtype this abstract XAI method type. It has to implement an analyze function, and it has to return an explanation, which once again is a very generic parametric struct that can contain almost anything. And the benefits you get from this is that you can automatically compute heat maps using vision heat maps and text heat maps. You can compose it with other methods that we have, such as input augmentations from explainable AI.jl. It's fully dependency free, which is very nice. It's super lightweight, and it makes it a good candidate for package extensions. So even if you don't plan on making your package part of this whole Julia XAI ecosystem, you can just put a package extension in there on XAI base and offer a way for your package to be used within our ecosystem. And yeah, that's more or less it. Do you have any questions?
All right. Thank you for the great talk. We have time for probably one question and one person with their hand up. So,
okay, that's two questions in one. Do you plan to include shap.jl? And second is, does that work with regressors as well?
So for now, we're focusing on classifiers. There are some extensions of these methods for regression models, but currently we don't implement them yet. I would be open to sort of include this in the ecosystem. On the question of SHAP, that's an open issue. I know there's already at least 2 packages implementing Shapley values. I think they're mostly focused on tabular data. In general, Shapley values are something that scales pretty badly for vision models, for example, because you have such high-dimensional data. But you could extend this on, I don't know, superpixels or similar things. That is absolutely something I would love to see happen. Yeah. Thank you for the question.
All right. Thank you, Adrian. Let's give everyone applause.
Maybe we can do some of the stuff at the hackathon. We don't have the other talk. Oh yeah. Here we go. What if the tabs are on?
Thanks. I just did a minor thesis in computational humanities. So explainable AI was something I actually know about in this whole JuliaCon, which is great. My supervisor is working on explainable AI in Python, and I've been trying to convince him for my entire year of my thesis to convert to Julia. And he's going, and I'm going to try and write a book companion in code. And he said, I'll do the Python, you do the Julia. Just learn Julia. It'll be better. So anyway, if you, I'd love to put him in touch with you if that's something you're interested in. He's a PhD student as well. Just about to finish up and doing a lot of stuff in explainable AI. Cool. So yeah, thank you again for the talk. It was really good.
Which methods are you currently using?
I believe the next talk is with Gajendra. Are you here? Sorry, sometimes this happens. Hopefully he's just running late.
He probably went to the compiler one.
Everyone's at the compiler talk, including our speaker.
I was going to go to that, but I'll just watch it later.
Oh.
There's the environment one. I'm going to go again.
Now is the LLMs, right?
What?
The LLMs talk?
There should be.
You're
I'm not
waiting for
sure.
a speaker?
Yeah.
Okay.
It's possible. I think this room's a little difficult to find. Sorry, everyone, we're waiting on the speaker. Hopefully they arrive, or someone can find them.
Yeah. Since you are volunteer, do you know why I should thank you for the financial assistance from trip?
Well, I'm trying to think who the right person is. From I think it's a starting. There's a couple starting points. If you run into Gareth Thomas, he's led the local group, so he's one of the ones that would definitely know. If he can't help you, he would know exactly who to talk to. Also, if anyone does want to watch this talk and doesn't have a long attention span for waiting, you can. I think that there's a door there that you can step out and watch the REPL stage until someone shows up. I could be wrong.
Can I just slide the door and then?
I think this one opens.
What do you say your name?
Yep. Gareth.
I guess
yeah.
he's on the Julia Slack. Maybe.
Yeah.
The next talk will start from.
So
Let me check.
the next talk is this is a 30-minute talk. So
Did you try to contact?
yeah, but we have.
Is the time change or?
So the real problem is that there's the compilers talk right now on REPL with Jeff.
Oh yeah.
That I think
Everyone's
there's about 500 of the 600 people all watching. We can turn this off.
recorded. So
intrigue people, or someone will close it.
We'll start at 4:31.
Yeah. Give everyone 1 minute to get inside.
Yeah, the guest talk
all my complaints with Julia are being solved at this conference.
Well, you're going to build one of them then.
And create many more. Can you see how many people are watching us online? 6. Well, yeah. Here's This the. started off with so few people that Yeah. it's just uphill. Yeah. Yeah. It can only get better. Yeah, exactly. Okay, yeah, here we go. I don't have a real introduction for you, so I'm gonna keep waiting. Okay. Or no, 31. So okay, so it is officially 4:31. So we can start now. I think hopefully some people will still come in, but this is Owen Lynch with computer algebra. So I'll hand it over to you.
Thanks. So this is GATLab, computer algebra, and standard ML modules combined. And let's get started. So this talk has 5 parts, and you're just gonna have to. I don't have section headers, so you're just gonna have to vibe when the parts actually shift. But so I'm gonna start and talk a little bit about the general context of the Algebraic Julia organization, which is a GitHub organization that we have a lot of packages in. GATLab is one of them. And then I'm going to say a little bit about the Topos Institute, where I work. Then I'm going to tell you, maybe give you a bit of a inclination as to why I have, why we developed GATLab and what kind of problems it solves. Then I'm going to give a short review of GATs. So GAT stands for Generalized Algebraic Theory. In Rust, they also have a thing called GAT, but it's called Generalized Associated Types, which is a little bit confusing. But and then I'm going to give a bit of a tour of some cool features in GATLab, and then finally talk about future work. GATLab is a refactor of the internals of CatLab. So, in one sense, you know, the internals of CatLab is a package that has been around since 2018, and we pass all the tests for CatLab. So, in one sense, we're somewhat stable, but in another sense, we did this refactor to enable a lot of new features, and but the focus was like we didn't want to maintain 2 separate versions of the GAT infrastructure, so the focus was on like make the new infrastructure, make sure it's backwards compatible, and then start doing some new things with it. And we haven't done too many of the new things yet, but they're exciting. But we've actually never given a talk. Well, so this is the second talk on GATLab. I gave another talk 3 weeks ago, but for like the 5 years that the GAT infrastructure in CatLab has been around, we've never actually talked about it so much. So hopefully this should be interesting, because you know this has been a core part of the core package in Algebraic Julia for a while, but now we're sort of starting to take it more seriously. So Algebraic Julia is a GitHub organization. We have a website, algebraicjulia.org. It's an informal collaboration between many contributors. We don't have a legal status. But mainly it's the Topos Institute and James Fairbanks' lab at University of Florida. The general mission of Algebraic Julia is to build a computer algebra system for category theory-based modeling. I won't get too far into that, but basically, like, category theory is a branch of mathematics, and category theory helps us figure out abstractions that can work across different modeling paradigms. So, you know, we do work in different domains like epidemiology or multiphysics or agent-based modeling, and we want to, like, sort of build abstractions for what does it mean to be a model, what does it mean to simulate a model, what does it mean to compose models, what does it mean to relate models, that will sort of work between different modeling paradigms so we can have a uniform interface and so we can reuse code. So I work for the Topos Institute. The Topos Institute is a registered nonprofit in Berkeley, California. We now, as of a week ago, also have an affiliate in the UK. And our mission is to shape technology for public benefit by advancing sciences of connection and integration. We do a lot of category theory, and part of Topos is developing the Algebraic Julia project, but we also do other things, which you can come find me and talk to me about them, but not in this talk. So why GATLab? So the thesis of GATLab is really that, you know, programming language research has been developing for, you know, years and years and years, but it seems like computer algebra systems are a little bit stuck in the past. Like, for instance, for instance, I want type systems. I don't want, like, you know, I have things that are more interesting than just numbers, right? So maybe I want to be symbolically working with matrices, but where the dimensions of the matrix are the dimensions of the matrix are symbolic, rather than having a matrix of symbolic numbers. Lexical scoping. This is a topic in, like, you know, this is a classic problem if you ever do compilers to do capture avoiding substitution, and when you just treat variables as symbols, this is quite tricky to do. But if you have a more advanced system for naming, for keeping track of variables, which we do in GATLab, then you can make capture avoiding substitution much more principled. And then structs. We should be able to have composite types in our computer algebra system, and you should be able to, like, you know, take in a struct of structs for instead of for, like, when you have a big thing and namespace things properly, etc. Lots of other things. So GATLab is sort of what I think of as a test bed to try experiment with stuff like this. And there's a lot of prior work in this area, which I won't go into too far, but these slides will be up on my website. I'll post a link after the talk, and it'll be under the YouTube video, so you can click on these links at your leisure. I will highlight CAP. CAP is Categories in Programming. It's implemented in GAP, which is Categories, Algorithms, and Programming, Groups, Algorithms, and Programming. Mohammed Barakat wrote CAP. I didn't know about CAP until about maybe, I don't know, 3 or 4 months ago, and I'm like, and it does a lot of the things that we wanted to do, but a lot better. So happens. But I want to shout out to them. And Mohammed Barakat, who writes it, is very nice. So what is the core idea? So now we're going to get into GATLab. The core idea behind GATLab is that there's sort of a hidden unity between two different things, which are ML-style modules, and if you don't know what that is, I'm about to explain it, and syntax trees. But so in standard ML or OCaml, if you've never seen it, so this is OCaml. Basically, this is saying that this is giving a module type, which is saying that a module of type semigroup must have a type T in it and must have a function which takes in two elements of T and returns an element of T. This is just OCaml syntax for a two-argument function. And now, so I can make a module which implements this signature, where T is set to int, and mapend is just plus. And I can sort of hack this into Julia. So one way, of course, would be to actually use Julia modules, but it's not very, Julia modules don't type propagate. The type of module is just module. So if I want to actually like make all of this run fast, I'm going to, instead of attaching all my functions to modules, I'm going to attach them to structs. So in this case, I'm going to have a zero field struct called plus semigroup, and then I can implement plus semigroup. I can implement mapend for plus semigroup, and that'll give x plus y. And the idea here is that this is telling me what the type parameter t is. And now I can make a function that is generic over the semigroup that I choose. And it takes in the semigroup as the first argument, and then some element here, and then it just doubles it. So if I pass in plus semigroup, then this will add these two, and if I have passed in times semigroup, then this will multiply those two. And we can we can model this mathematically by a thing called an algebraic theory. So an algebraic theory consists of a collection of type symbols, a collection of function symbols, each of which has a signature. So something like it has a bunch of sorts, which are the arguments, and then it returns a sort, of types, and then a collection of laws, which give equations. So this says like for all x1 in S1, blah blah blah, xl and SL, this term, which involves these free variables, is equal to that term. And algebraic theories are part of a branch of math called universal algebra, which has a long history, but the most exciting part of that history is William Levaire's 1963 thesis, which I encourage you to check out. If you just search Levaire thesis, it'll come up. And so here's an example. The algebraic theory for monoids. Monoids are a theory which extends semigroups. It has a single sort T. It has a function symbol M, which was what we were calling mapend before, which takes two elements of T and returns a T. And then it has a function symbol E, which takes no elements and returns a T. And then we have these laws. So E is an identity with respect to M, and M is associative. So we can sort of translate that mathematical definition into Julia. So we can just make an extremely simple algebraic expression type. You have the head, which is supposed to be a function symbol. I'm using symbols here, even though I said I wanted to do proper lexical scoping, but this is just to fast and dirty approach to give you the idea. But so yeah, so this is just like a very simple algebraic data type. Then I can give a signature, just has like a vector of arguments and then a return type. An equation has a context, which has a list of like the context has like symbol and what type that symbol is. So a variable and what type that variable is, and then two algebraic equations that I want to be equal. And then finally, an algebraic theory just has a set of symbols, a map from function symbol, a set of type signals, a map from function symbol to the type of that function symbol, and then a collection of equations. And yeah, and basically in GATLab, we have a macro to declare a significantly more advanced version of this, and it looks like this. So I declare t as a type, I declare some function symbols, and then I declare these axioms. And I get out a data structure. I also actually get out a module named theorymonoid that has theorymonoid.m and theorymonoid.e as functions. And these are the functions that I'm going to overload when I make models of the theory of monoids. So what is a model of an algebraic theory? Well, a model of an algebraic theory with sort symbols, function symbols, and equations consists of a type for each sort symbol, and then a function for each function symbol that is of the correct function type. And such that when I take each of my equations and replace each of the function symbols with an actual function and then do the universal quantification over the context, then the equation becomes true. So for instance, there's a model int plus of the theory of monoids where I interpret t as the type of integers, I interpret m as plus and e as 0. But there's also for every little n, there's a model of the theory of monoids where which is the integers mod n. And there's also a model of the theory of monoids with strings and concatenation. Or you can do real numbers with min, or real numbers with max, or subsets with intersection or union. So this is what I was saying at the beginning. I want to move computer algebra not away from just real numbers to these sort of either richer or less restrictive theories that have interesting models that are not necessarily real numbers. For instance, or yeah, well, in this case, you know, I might be using real numbers, but maybe I want, if I'm doing like convex optimization, I want to do computer algebra with, instead of plus and times, I want to do computer algebra with min and plus, which doesn't form a ring, it forms a semi-ring. But I can do all sorts of algebraic simplifications there, and that's sort of an interesting thing that I might want to do in a computer algebra system. So what does it actually look like now to declare a model of a GAT in GATLab? Well, so previously I showed sort of like zero field struct models, but there's nothing actually to stop you from putting actually interesting values in your model struct. So this is like a parameterized model, which is parameterized by the modulus. So I have a model of the theory of monoids, which is the integers mod n, and I get that n parameter there. And now I can declare the instance, and I'm actually doing theory of groups because I also want inverse. So you know, you can see here when my implementation for the, well, okay, I've sort of changed things up, but now I'm calling this dot instead of m. I'm going to use x plus y, but then mod out by the model.n. And now I can actually use this with model macro, which basically it's kind of like import using, or it's kind of like using. So this is like using zmod n e dot. What this does is it just wraps this in a let binding that binds e and dot to anonymous functions that pass in zmod n7 as its first argument. So those are algebraic theories. Oh geez, I'm not doing well on time at all. What are generalized algebraic theories? Well, it's kind of like a algebraic theory, except like I said at the beginning, it has dependent types. So what's an example of something that you might want to do with this? Well, like I said at the beginning, you might want matrices. You might want to do symbolic algebra over matrices, but where the dimensions of the matrices are also symbolic. And you can do that with GATLAB. You can declare some types. I'm declaring a type of dimensions, a type of scalar, and a type of matrices, which depends on 2 dimensions. And then I can write out the type of matrix multiplication, and note that here this n has to be equal to that n. Maybe I should be using my mouse so that it's on the recording. Oh well. And so, but then for plus, they actually have to be the same dimensions. So that's cool. Let's keep going though. So how to work with GATs in general. So they're a bit of a hairy beast because if you want to type check that 2 GATs are equal, that might like 2 types being equal might mean that I'm checking the type parameters of those types, and the type parameters of those types are arbitrary terms. So now I have to decide if those terms are equal, and I have to solve like a word problem to do that, and that is in general undecidable. So that is sad. But we won't give up. So first of all, we can conservatively type check. So we can say, according to, maybe if you like apply the laws of this theory, then I can prove that these 2 things are equal. But actually, I'm just going to reject your program unless they're equal without having to do any of that rewriting. Or maybe I have some limited rewriting. Or I can just derive runtime assertions from this. So like screw static type checking, but from this I can say, okay, well when I multiply matrices, now I have to check that their dimensions are equal at runtime. Or we can just use these as like a contract and derive property tests. So whenever I have a model, I can use the equations of this theory and just like maybe just try to generate a bunch of random elements and then check if the equations hold. So yeah, so that's sort of how we wiggle around this problem that type checking for GATs is undecidable. And so now I'm just going to go through a bunch of some cool features of GATLAB and then finally talk about future work. So one cool feature about GATLAB is that so when you do category theory, whenever you learn about a new thing, you always ask, well, is there a notion of morphism between these 2 things? And for GATs, there is. So basically, I can write a morphism from the theory of So the theory of arithmetic, this is like piano arithmetic. So I have like a function symbol for successor, a function symbol for plus, and a function symbol for times. And then I have these laws which say how successor interacts with plus and times. And now from my theory of monoids, I can go ahead and say, I'm going to make a map from theory of monoids to theory of arithmetic where I'm going to interpret the operation here as plus in piano arithmetic or as times. And what this allows me to do is if I have any model of the theory of arithmetic, which may use actually something other than the natural numbers, which may interpret. Then I can pull that model back along the theory map, and get a model of the theory of monoids. Some other things. So, CATLAB, algebraic Julia, we want to do declarative modeling. So here's GATLAB being used for declarative modeling. So this is similar to, MTK, but you notice I have this parameter theory ring. So I can change the GAT that I'm working in, and that changes the kind of operations that I'm allowed to use in my models. So in the theory of ring, I can just use plus and times. If I could extend the theory of ring, maybe to add like sine and cosine, and then I could use sine and cosine. And this is useful for declarative modeling because I can know up front like what operations I have to support. So if I want to like move this cross language or compile it to a certain thing, I know up front the operations that I'm going to need. Yeah, so, and, oh yeah, and it runs. You can get a little, nice little spring with gravity attached running out of this. Now, and this is using undirected wiring diagrams out of the hood and resource shares. There's a paper on that. This is work by Sophie Libkind. And so, okay, so now future work. So sort of the big fish for GATLAB development over the next couple of years is, or the next couple of months actually, is we want to use the typed computer algebra to do partial differential equations. And now there's a lot more types in partial differential equations than there are in ordinary differential equations, especially if you do them the way that we want to do them, which is with the discrete exterior calculus. So that's what the DEC in Decapode stands for. And this allows you to do all sorts of fun multi-physics problems. But I want to keep, and I want to do multi-domain, multi-scale, multi-physics. So I have multiple spaces, so I have to type a variable by like, is this a 2 form, a 1 form, whatever? What space does this live on, etc. I might have morphisms, smooth maps between the space. So for instance, I include a boundary into the space, which is like a 1D manifold and a 2D manifold. Anyway, so there's a lot of use for typed computer algebra in this setting. More future work is rewriting. I've actually implemented eGraphs twice for GATLAB. Each time they have been swamped and gone unmaintained by other features that I added to GATLAB. They've never really like caught on, and I have never really liked the design. But I have a design which I think I like now, which is that you put in a mutable eGraph. Well, anyway, I won't go into that. But it's a cool design. And future work is interoperability. I want to be able to interoperate between models that I write down in Julia and maybe some other programming languages. And the sort of closed world assumption of my expressions, like I was saying before, that I know statically, like, oh, okay, I'm working in the theory of rings. It's only plus and times. I'm working in the theory of rings plus trigonometric functions. It's only plus times cosine. That helps with moving cross language. And that's the end. So, yeah, thank you.
All right. Am I on? No. Okay. Let's see. Yeah, okay. Thank you very much for the talk. It was great. We have time. Well, we're sort of out of time, but this is the last talk here, so we do have time to do questions. But if you have somewhere else to be, we are over time, so you are free to leave. Oh, wow. By how close we are.
Have you also been looking at real algebraic geometry? Is this somehow related to your work?
Is real algebraic geometry like like is that like algebraic geometry with inequalities as well as equalities?
Yes, yes.
It's cool, but I have not been looking into it. Yeah, I mean, this is mostly focused on equalities, actually. Yeah.
Okay, so I was playing with this library 1 month ago, and I was looking into the Occam-like modules part of it, and I wanted to encode queues in Occam style with axioms. And then I encountered a problem that the algebraic specification for queues uses if statements, like when the queue is empty, then you return something different than when the queue is not empty. And maybe you have some idea how to properly encode those ifs in equations, because I can provide 2 different implementations of ifs and include them in the type of the module, but it looks ugly and it drowns in boilerplate, like if for returning elements and if for returning new queue from tail. It's not optimal. And do you have any idea how to properly encode it, or maybe you need to somehow extend the library?
Yeah, well, it seems like to me the thing that you would want for that is like optionals, right? Like, you know, union, sum, t, nothing. And in order to do optionals, you need generic types and sum types, neither of which GATLab supports. Because, well, because we haven't gotten around to it. I mean, it would be cool, but the thing about adding sum types is that it actually restricts the class of models that you can use. So it's like, you know, more features equals fewer modules, or fewer models. But in the context of like just using this as a module system for Julia, that definitely makes a lot of sense. So, yeah, it's but maybe if you want that, just use OCaml.
Yeah.
OCaml's great. I love OCaml.
I mean, there are so many languages out there that have are equipped with better type systems to do this kind of things like Haskell or OCaml, or
yeah.
What drove you to do this in Julia?
Well, so there's a couple things. So one, you can do algebraic theories in OCaml. You can't do generalized algebraic theories because OCaml is not dependently typed. And I think generalized and the other thing is that really like what's going on here is it's not just a module system, it's also a computer algebra system. Like whenever you declare a theory, you don't just work with models of that theory, but you can also work with like syntax trees in the language of that theory, and sort of do rewriting like in Julia of syntax trees, and that's not so much of a thing that you can do. Like when you write down a model in OCaml, you don't also get syntax trees for that model, and you don't really get, and you don't have laws in OCaml, so it wouldn't make sense to like do egraph simplification on you know, the instances of that, and there's actually, it almost makes more sense to do GATs in specific as a computer algebra system, because in a computer algebra system, if you implement it with egraphs, you're sort of iteratively like figuring out new equalities via rewriting between your elements, and like via like finding new equalities, now terms might type check when they didn't before. So you know, you can say like, you know, the user puts something in, it doesn't type check, and you give out an error message like this doesn't type check, and the user can be like, oh, you need to apply this axiom, and the user says, okay, apply this axiom, and then two things unify, and then you try it again. Oh, now it type checks. So there's like a lot of, it's a different vibe.
I've heard of Idris, for example.
Yeah.
Where basically the implementation of your function is the proof of the theory that you. I don't know.
Yeah. No, I mean I love Idris. But the idea of GATLAB is that sort of the expressions that make up GATLAB should be interoperable. I don't want to embed a entire Idris interpreter into JavaScript.
Was there one more question? Or that? Okay, we got all the questions.
Cool.
Thank you very much for the talk. Maybe last round of applause and. For I think this room, unless someone correct me if I'm wrong and.